Hello everybody. So we'll be starting off with number systems today. This is the one of the most basic and the foundational topics in all of the SSC syllabus that you'll do. Okay, so we'll be talking a little about numbers. What are actually numbers? Numbers are nothing but mathematical operations. Okay, these are nothing but math operations which help in counting. Okay, these operations help in counting or quantifying numbers or quantifying things. When I say quantify, let's assume that we are supposed to count or we are supposed to measure how much rice is present in a bowl. So what numbers help us to do is that we need not check each and every grain of rice. We can't say that there are 10,000 grains of rice in this bowl, but we can use a different number. Let's assume we can say that there are 500 grams of rice. So what does this 10,500 quantify, or what does it measure? It actually measures the amount of rice kept in this bowl. Okay, so number systems has this thing which it helps, or numbers basically helps us quantify things. So this is the most and the most standard and the most basic thing which everybody should be able to understand. Coming down to types of numbers, there are multiple types of numbers in with us. The first one being natural numbers. Okay, see, numbers start from 0, 1, 2 and go on till infinity. There is also a concept of negative numbers. Okay, it goes from negative infinity to 0, then from 0 to positive infinity. So this is see, these are just things which might be asked in the exam. There is a good possibility that a few numbers are written in the exam and they ask you what kind of numbers these are. So I'll be telling you all of them in very short, so that you understand the most basic part of it, so that you can you can still have some energy to focus on the bigger things. Okay, on the more difficult concepts which are asked in the examination. So the first one being natural numbers. What happens with natural numbers? In natural numbers, these are nothing but counting numbers. Okay, these are nothing but counting numbers, and they start at 1 and go till infinity. There is no concept of positive, negative, or even 0 in natural numbers. Got it? Coming now to point number 2, there are whole numbers. They are whole numbers. See, what happens in whole numbers is that they are definitely used for counting as well, but they start from 0. In natural numbers, we did not have a chance to start from 1. In natural numbers, we did not have a chance to start from 0, but in whole numbers, we have a chance that things start from 0, 0, then 1, until infinity. Again, in natural numbers as well as whole numbers, there is no concept of negative numbers. Okay, there is no concept of negative numbers in this. Coming now to the third point, when quantities or the absence of a number was supposed to be shown, or the absence of a quantity was supposed to be shown, a need was felt to introduce something called integers. Okay, something called integers. So what happens in integers is, what happens in the case of integers is denoted by the word z, okay, or z. Natural numbers is denoted by the word n, and whole numbers are denoted by the word w. Okay, why isn't I, like in this case n was used for natural numbers, w was used for whole numbers, why isn't I used for integers? The reason being this, that capital I or maybe small I is used in the case of imaginary numbers. In case of imaginary numbers, when the value of I is equal to root minus 1. Okay, root minus 1. Root of any negative number is undefined, but still the root of minus 1 is defined. Okay, the root of minus 1 is still defined. So integers call themselves as z, and there is a concept of negative infinity, and there is a concept of negative numbers. It starts from -1 to -2, then -3, -4, and so on till minus infinity. Then at 0, there is the center point. Then there are positive numbers. We don't call them +1 particularly, but we call them regular numbers. Okay, we call them regular numbers, and they go till positive infinity. Okay, positive infinity and negative infinity. So I think this is, the entire picture is pretty much clearly painted of what integers are called for and why integers are actually used. Coming down to my fourth type of numbers, the fourth type of numbers are rational numbers. The fourth kind of number are called rational numbers. So Rational numbers are those kind of numbers which can be put in fractions, which can be expressed in the form of fractions. So what are fractions? Fractions are nothing but numbers which can be expressed in the form of numerator upon denominator. Okay, they can be expressed in the form of numerator upon denominator. So these are fractions. These are fractions. Let's assume 2. So you'll ask me that no, 2 can't be expressed in the form of numerator and denominator, but the reality is 2 can be expressed as 2 upon 1. Let's say 2.5. 2.5 is nothing but a decimal number, but it still can be represented in a fractional format, which is 5 upon 2, which is 5 upon 2. So rational numbers are nothing but fractions which can be represented in the form of numerator upon denominator. And there are other two prerequisites to call them rational numbers. The first one being they have terminating decimals. They have terminating decimals. And number 3, and number 2, they have recurring decimals. They have recurring decimals. Somewhere down the line, I'll tell you what terminating decimals and the recurring decimals mean. But in short, I'll just tell you that terminating decimals is a point when the quotient doesn't go beyond the specific number. Let me tell with the example of 5 by 2. When you divide 5 by 2, you get an answer which is 2.5000, or n number of zeros you can put over here. But the essence of things would not change. The essence of things would not change. It will still remain 2.5. So this, at this point, after 2.5, we are not getting any number which is natural in number. We are not getting any natural number beyond 0.5. So here we call it terminating decimal. We call it terminating decimal. But what about recurring decimals? Recurring decimals are the kind of decimals which keep on occurring again and again. Let me do it by 1 by 3. Anytime we get a prime number in the denominator, no, I wouldn't say prime, but let's say like we get numbers like 3, 7, 11, and even 9. Okay, when these kind of numbers come in the denominator, at that time, you will not be able to figure out if any new decimal is going to come up or not. Let's assume that 1 is divided by 3. When 1 is divided by 3, the answer comes out to be 0.3333 and so on. This number 3 is not going to change. Till infinity, you will find 0.3333 and going on. So at this time, I can easily conclude that the terminating decimal, there is no terminating decimal, but there is recurring decimal. Okay, there is a recurring decimal available, and this recurrence of 3 calls it as a recurring decimal, and it also counts in as rational numbers. All right, so I think that is pretty clear. Then talking about irrational numbers. Okay, so irrational numbers are those kind of numbers which cannot be expressed in the form of fractions. So they cannot be expressed in the form of fractions, and they have this other prerequisite of being non-repeating in nature, and they also have this property of being non-recurring in nature. Non-recurring in nature. When this kind of a quantity comes up, non-repeating and non-recurring, that time we can call it as irrational. Let's assume root 13. So when you have root 13, or let's assume pi for that matter, pi is definitely rational, but just kind of remember that there are 100 distinct values of pi, 100 distinct decimals of pi. When I say 3.14, it goes on 3.141217, and it goes on, and you will not find a fixed pattern to be there. So you can't call it repeating anymore. You cannot call it repeating anymore. And what about recurring? And there is no recurrence of new numbers as well. Non-repeating, or I should rather say non-terminating. Okay, this is non-terminating. They are non-terminating in nature. They would never terminate. Okay, they would never terminate. So these are the most standard forms of numbers which we are talking about. Then talking about complex numbers. Complex numbers are such numbers which can be represented in the form of a is to a plus iota b, and iota being the value which I've already discussed over here of that of I being equal to minus root 1 or root of minus 1, not minus root 1, root of minus 1. Complex numbers is something which we can discuss in the later part of the chapter. So we've already learned about complex numbers. We already learned about complex numbers, and the only thing which you need to know about complex numbers is that iota is used, and the value of iota is nothing but root of minus 1. Then on the seventh type of number, we have prime numbers with us. Okay, so I'll take you to the next slide. Prime numbers are those kind of numbers which cannot be split into more factors other than one or itself. What does factor actually mean? Factor means reason. And when I say, let's assume there's a number 6. Now, what is the reason that 6 could form itself? And if I say that I need to break down the prime factorization, or I need to take out all the prime portions out of 6, so there would be 1, there would be 6. So this is basically 1 and itself. This is basically 1 and this is itself. So these two factors are always going to exist. As long as a number is present in the world, whenever it is multiplied by 1, it would come out to be itself. So 1 is a factor. And whenever the entire number is there, that is 6, so it is a factor of itself. So these two numbers are always going to remain if a number remains in existence. If a number remains in existence, these things are always going to stay. But if I break it down and I try to find out more reasons, more chances of creating 6, then the value would be 2 and 3. The value would be 2 and 3. All right. So 6 could be broken down into 4 pieces, 1 and itself, and into 2 and 3 as well. So 6 is not a prime number. This is what tells that 6 is not a prime number. Let's talk about, let's say, 7. Now, if I try to break down 7 into multiple portions, then the only two portions I can break down 7 into are 7 and 1. There are no other smaller factors which 7 can be broken down into. So this is a prime number and this is a okay. So there is no so these are non-prime numbers. Okay, these are non-prime numbers. Non-prime numbers can also be called as composite numbers. As composite numbers, there is no, like, these are just composite numbers, and these are prime numbers over here. Okay, 7 and 1, 7 and 1, 6, 3 and 1. So this is all in place. Okay, so these are the major kind of numbers which you need to know. There are just one or two more kind of numbers which are co-prime numbers. Then there is another kind of number which is called a perfect number. There's something called a perfect number. So when I talk about co-prime numbers, this means that there are two numbers a and b, and there are no common factors. No common factors except 1. So there are no common factors between a and b, and this is what makes it co-prime. Okay, so when two numbers are co-prime, that means that they are friends and they don't have any common factors between them. Then we'll talk about perfect numbers. See, what are perfect numbers is, let's assume 6 again. Okay, don't think that 6 is my favorite number. It's just that 6 falls into so many categories that this example is universal in nature. Okay, this example is universal in nature. So if I have 6 over here, 6 can be broken down into its multiple factors, which are 1, 2, and 3. Except the number itself, there are 3 factors of it. If I take a sum of these 3 factors, it is going to be 1 plus 2 plus 3. So 1 plus 2 plus 3, we have 3 factors and all of them sum up to 6. So when the number which is n and its factors also sum up to n, so that kind of a number is called a perfect number. Okay, that kind of a number is called a perfect number whose factors sum up to itself. I think 28 is also one of them. Let me check. I'll talk about 28. I'll talk about all the factors of 28. 1, there is 2, there is 4, there is 7, and there is 14. Okay, if I add all of them up, 7 plus 3 is 10, 10 plus 4 is 14, 14 plus 14 is equal to 28. So yes, 28 is a perfect number. All right, 28 is a perfect number. This has been very well established. Now, the first example which I'm going to solve is here on the left hand side. What is the mean of the first 10 prime numbers? See, prime numbers start from 2 and they can go till infinity. And there are three very important outcomes which I need to talk about. The three important outcomes are that the number of prime numbers between 1 to 50. The number of prime numbers between 1 to 50 is 15. The number of prime numbers between 1 to 100 is equal to 25. And the number of prime numbers between 1 to 200 are 46. Okay, so these are just some raw facts which can be asked to you in the examination. Coming back to my question, we need to talk about the first 10 prime numbers. Starting from 2, 2 is the only prime number which is even in nature. Also, 2 has only two factors, which is 1 and itself, that is 1 and 2. So 2 is the only prime number which is even as well as prime. So I'll start from 2, then 3, then 5, then 7, then 8 is not 7. Yeah, 7 we have, 8 no, 9 no, 10 no, 11 yes, 12 no, 13 yes, 14 no, 15 no, 16 no, 17 yes. Are we done with the first 10? We are 3 plus 3 6 and 4 are left. Okay, so 17 is one of them. 18 no, 19 yes, 20 no, 21 no, 22 no, 23 yes. Okay, I think we are good. No, 3 3 3 and 3, just one more to go. Okay, 23, there's 24 no, 25 no, 26 no, 27 no, 28 no, 29 yes, 29 a definite yes. So these are all the prime numbers and we need to find out the mean, and that too of the first 10 prime numbers. Okay, we need to find out the mean of the first 10 prime numbers. So these are my 10 prime numbers and I believe we are good to go. Let's quickly add all of them up, and after adding all of them up we need to divide it by 10. Why do we need to divide it by 10? Because in this concept it is talking about the mean, it is not talking about the sum. So we need to simply divide all of them together by 10. So 2 plus 3 5, 5 plus 5 is 10, 10 plus another 20 is 30, 30 plus another 30 is 60, 60 plus another 40, 60 plus another 40 is 100, and 100 plus another 29 is 129. So we are sitting at 129 upon 10 and the average comes out to be 12.9. Okay, so the average comes out to be 12.9, which is the mean of my first 10 prime numbers. Good to go. Moving to the next question. Determine the product of first 5 prime numbers. Okay, yeah, so to determine the product of the first 5 prime numbers, okay, we need to simply quickly come up with the first 5 prime numbers, starting from 2, then 3, then 5, then 7, then 11. Okay, 2 3 5 7 and 11, these are the first 5 prime numbers. I need to quickly multiply them. 5 2s are 10, we have a 0, 3 7s are 21, 21 11s are 231, so 2310. And this question was as simple as that. And this is not a question which I generated, this was one of the PYQs. Okay, so this was one of the PYQs that we've been seeing for a very long time. Good enough. Moving to the next question. Which of the following is a prime number? So to determine which of these one of the four numbers is a prime number, we need to focus on one very major point. And one of those major point is divisibility rule. Divisibility rule. And there are multiple divisibility rules for different numbers, and the few of the standard ones I will talk about. Okay, I'll talk about 2, I will talk about 3, I will talk about 4, and I'll talk about 5. Okay, so I think these are good enough and these are standard enough. I will be talking about 7 in the later times, as well as 11 as well. Okay, there is going to be 7 and there is going to be 11 as well in the later times. I think to solve this particular question, these three are good enough. Whenever I need to check if a number is divisible by 2, I need to check the unit digit. If the unit digit is divisible by 2, that means the entire number is divisible by 2. Simple enough. Good. Talking about 3 here. For 3, I need to check if the sum of all digits, if the sum of all digits is divisible by 3, and if that is the case, then the number is divisible by 3. Talking about 5 over here, talking about 5, there are two things to be seen. If the last unit digit, if the unit digit is either 0 or the unit digit is 5, okay, either 0 or 5. If this is the case, that 0 and 5 are present, at that time we can say that it is divisible by 5. Okay, so quickly applying all these methods to the options here. Okay, 7 plus 7 is 14, 14 plus 1 is 15. If the sum is 15, it is divisible by 3, leaving no remainder. So this is not a prime number. When I say prime number, it should be only divisible by 1 and itself. As I can clearly see that none of the digits, none of the options has the last digit to be divisible by 2 or even. So none of them would be done with 2. So that's why I'm using 3 for my rescue. 7 plus 1 is equal to 9 and it is divisible by 3. That is why this is also not a prime number. We only have two options to go, 161 and 193. Okay, we have 161 and 193. For 5, I don't think there's a possibility because I can't see a 0 or a 5 in the unit digit. Coming down to 7, I will manually do it for 7 because I really want you to know the divisibility rule for 7 at a later stage. Okay, so 7 2s are 14 and 7 3s are 21. 7 2s are 14 and 7 3s are 21. So when 7 is multiplied by 23, that's when I get 161. This means that 161 has more factors. 161 has more factors available. More factors means 161 has 4 factors. The first one being 1, the second one being 7, the third one being 23, and the fourth one being 161. So it has 4 factors. That is why it is not prime. The only number we are left with is happily 193. So out of the 4 examples, after doing a little bit of hard work, I was able to find out that 193 is the prime number of all those numbers. Okay, out of all the 4 options, this is the prime numbers, and we'll be coming down to the concept of unit digits in the next video. All right, see you very soon. So we'll be starting now the concept number 2, which is the concept of unit digits. First, I'll tell you what digit actually means over here, or what unit digit actually means over here. Let's assume there is a number which is 9, 8, 7, and 1. Okay, so this is the entire number. How would a child, how would the children who have recently started learning about numbers call it? They would call it 9,871 rupees. Okay, so when you add all of them up, you get 9871. So the number out of all the 4 numbers which can stand alone without the help of a 0 is called the unit. Okay, and the one over here which has a 0 at the back is called the tens digit. This one 8 is basically the hundredths or the hundredths digit. Okay, ths digit, and this is the thousands digit. This is the thousands digit. So what we are actually trying to do over here is we will get complex problems in number systems which says that 2 raised to the power 91, you need to find out the unit digit of this number. Or let's say 2 raised to the power 10, find out the unit digit of this number. Whenever you encounter such a problem, you are not supposed to multiply 2 with itself for 10 times. Okay, this exercise is not required. Similarly, you cannot multiply 2 with itself for 91 times. This heavy exercise or this sort of a labor work is not required in the examination. You have to find out a shorter way to solve such questions. And to our rescue, to help us, there is a concept called the concept of cyclicity. The concept of cyclicity. Okay. The concept of cyclicity says that the unit digit repeats itself. Okay. The unit digit repeats itself. What do I mean to say when I say it repeats itself? It means that with each and every exponential growth, there is a sure shot guarantee that there would be a repetition in unit digit. Again, this seems to be a little complex, so I'll help you with the example of 2, then 7 and 5 and 3. Okay, and here I would be writing the power or the exponent it is raised up to. Okay, I'll go till 8, and I don't think it should be a very difficult task. Okay, 2 raised to the power 1 is 2, 2 2s are 4, 2 2 square is 4, 2 raised to the power 3 is 8, 2 raised to the power 4 is 16. Then this again goes to 32, 32, then 64, then 64, then 128, then 256. Similarly, if I do a 7 square, it is 49, then it is 39, no, 343, yeah, 7 nines are 63, then 6 here, 7 fours are 28, 28 plus 6, 343. Okay, this is 343. Then another 7 is multiplied here, that would give me 1. Another 7 is 7, 7 sevens are 49, 7 nines are 63, 7 threes are 21, 7 sevens are 7 ones are 7. Okay, so this is nothing but the unit digit. Then 5, the square of 5 is 25, the cube of 5 is 125, then another raised to the power 3 is 625, then another 5 is 15625, and so on. Okay, you'll always see a 5 at the unit digit of 5. Then coming with 3, 3 ones are 3, then 3 square, 3 threes are 9, 3 nines are 27, 3 27s are 81, 3 ones are 3, 3 eights are 243, then another 3, 3 fours are 12, and 3 what, this is going to be 729, no, 3 threes are 9. Okay, this is going to be 729. So you would see that there is a pattern that is being followed over here. This is the first instance, second instance, third instance, and fourth instance. If you see, this 2 over here is now getting repeated, 2, 4, 8 and 6. Okay, so this is 1, 2, 3 and 4. This means the cyclicity, or the cycle in which the exponents of 2 would repeat itself, is equal to 4. Similarly, checking it out for 7, this is 7 ones are 7. Okay, this is the first one, second one, third one, fourth one. Then again, first, second, third and fourth. So this means after every 4 instances of exponents, it would repeat itself. So the cyclicity of 7 is also equal to 4. Checking out for 5. Each and every time the 5 is repeating itself. Okay, it's coming over and over again. This means that I'm getting 5 all the time. This means the cyclicity is equal to 1. Checking it out for 3, the cyclicity of 3 is, this is 1, 2, 3 and 4. Number of distinct digits, we are finding out the number of unit digits which are distinct in nature. So 1, 2. Again, after every call of 4, we are getting the repetition of unit digits. If I try to do this for all the prime numbers, the maximum cyclicity, the maximum cyclicity I would get is that of 4. Okay, the maximum cyclicity of that is that of 4, and the minimum cyclicity is that of 1, which I have easily seen in the case of 5. So with the use of this max cyclicity, what I am going to do is, let's assume that 2 raised to the power 10, the unit digit was supposed to be found out. I know that the value of 2 raised to the power 10 is 1024. So what I do is I take this power 10, I take this exponent 10 and I divide it by 4. When I divide this exponent by 4, I am getting a remainder. I am getting a remainder which is that of 2. I get the remainder of 2. So what I'm supposed to do is I'm supposed to plug in that remainder and put it back here like this. So whatever is the unit digit of 2 raised to the power 2 is going to be the same unit digit of 2 raised to the power 10. So 2 raised to the power 2 gives me 4 and the unit digit is 4. So it is going to match with the unit digit of 2 raised to the power 10 because I'm matching the remainders. Okay, I'm matching the remainders. Now, there can be a possibility that 2 raised to the power 4 comes into the question. 2 raised to the power 4 comes into the question. Now I'll use this 4 and divide it by 4. When it is getting completely divided, the remainder comes out to be 0. The remainder comes out to be 0. Whenever the remainder comes out to be 0, I am not supposed to consider it to be 2 raised to the power 0 because that would give me the unit digit as 1. This is the wrong way of solving it. You have to assume that it is 2 raised to the power 4 itself, and which would give you the cyclicity or the unit digit as equal to 6. Okay, as I've already pointed out over here, 2 raised to the power 4 is equal to 6. So the unit digit of 2 raised to the power 4 is going to be 6. Okay, if any number, let's assume 2 raised to the power 24 comes into the picture, I can easily see that 24 is completely divisible by 4, leaving a remainder of 0 with me. So I can easily say that 2 raised to the power 4's unit digit, which is equal to 6, is going to be the same unit digit of 2 raised to the power 24, and the unit digit is going to be 6 again. Okay, whenever the remainder is 0, the unit digit would be considered that of raised to the power 4. Okay, I hope I've made myself very clear. So we are through with this concept of cyclicity. Each and every time we are going to divide the exponent with the value of 4. Okay, we're going to divide the exponent with the value of 4. Why? Because 4 is universally acceptable to all cyclicities. The maximum cyclicity of any number, of any given prime, non-prime, whatever number we have, it is definitely going to be of the same cyclicity of 4 whenever it is given any exponents with it. Okay, whenever it is raised to any new power. So I'll divide the thing with 4. I'll use the remainder and then I'll proceed. Okay, moving on. What would be the unit digit of 382 raised to the power 575? I'll quickly write down all the powers of 2. Okay, and I'll do it only 4 times, 4 or 5 times at max. Okay, 2 raised to the power 1 is 2, 2 is 4, 3 is 8, and 4 is 16, or unit digit is 6. Then it again comes back to 2. Okay, so this is the power 1, power 2, power 3, power 4, power 5, and so on and so forth. Now I'll be using the same concept of cyclicity and would have the exponent available with me, exponent or the power available with me. I'll divide this power quickly by 4, which would give me 4 ones are 4, 4 fours are 16, and 4 threes are 12. This is the quotient, and the remainder that I'm getting out of it is equal to 4 threes are 12, right? So the remainder I'm getting out of it is 3. This remainder I would use and apply it to the power of I'll apply it to the power of 3 again. Okay, I'll just quickly use the unit digit over here. The unit digit is that of 2 and the remainder is 3. So the same unit digit of 2 raised to the power 3 would be the unit digit of 2 raised to the power 575, or this entire question itself. So 2 raised to the power 3 is equal to 8. This is the unit digit. Now this unit digit is going to be the same as that of 382 whole and 575. The unit digit of this is equal to 8. See how easily we could solve the question. Moving to the next point. if x is equal to 164 raised to the power 169 plus 3 plus triple 3 raised to the power 337 minus 727 raised to the power 726, then what is the unit digit of x? Let me quickly dissect my problem into three parts. This one being part A, this one being part B, and this one being part C. Okay, I have 164 with me, I have triple 3 with me, and I have 727 with me. I'll quickly write down the exponents. 4 ones are 4, 4 fours are 16, 16 fours are 64. So this is following a cyclicity of 2. Okay, this is following a cyclicity of 2, and the first power, second power, third power, and fourth power I've quickly written down. Again with 3, we know with 3, 3 threes is a 9, 3 nines are 27, 3 sevens are 21. These are the four powers of 3. Okay, these are the four powers of 3, and the cyclicity being followed is that of 4. Similarly with 7, 7 ones are 7, 7 sevens are 49, 7 nines are 63, 7 threes are 21. Again, it is following a cyclicity of 4. Okay, following a cyclicity of 4. The cyclicity doesn't really matter because we are going to use the standard cyclicity, and we are assuming that all the numbers with us have a cyclicity of 4. So now I'll quickly move to the exponent. The exponent of 164 is 169. When I divide it by 4, I get the remainder to be, see, 4 4s are 16, 4 2s are 8, I get the remainder to be 1. I'll use the exponent of triple 3, which is 337 divided by 4. The remainder would be 4 8s are 32, 4 4s are 16. Yeah, 4 8s are 32, 4 4s are 16. I'll be left with the remainder equal to 1 again. Similarly, 727 has an exponent of 726. I'll divide it by 4. 18 fours are 72, and 4 ones are 4. So I would be left with the remainder of 2. So what am I supposed to do with it? I am supposed to have it as 164 raised to the power 1 will have the same unit digit. So the unit digit is 4. Triple 3 to the power 1 would have the same unit digit, which is equal to 3. And 727 would have the same exponent of that of 2. Okay, that of 2. Now now 7 square 7 square is 49, so the unit digit is 9. I have these three outputs with me. Now I will apply the operation of plus and minus with them. The operation says 4 plus 3 minus 9. 4 plus 3 is 7. 7 minus 9 is minus 2. Whenever you get a minus 2 over here and you're working on the unit digit, this minus 2 cannot be the unit digit. It only has to be a positive number. Every time you encounter a minus 2, this is going to be used in carry. Whenever there is a situation of carry, what you do is you add 10 to the situation and subtract the 2 out for the situation, or subtract whatever the unit digit you are getting over here. This would give me an output of 8, and the value of 8 is going to be my unit digit of x. Okay, this is going to be the unit digit of x. I'm following the same concept over and over again. The only new thing which I found out was every time you find a negative unit digit, try to add to 10 with it. Had it been a minus 9, I could have added plus 10 with it and would have gotten the unit digit as 1. In this case, we have minus 2. We are going to add 10 to it, and 8 is going to be my new unit digit. All right, moving on. What is the unit digit of 1 raised to the power 5, 2 raised to the power 5, 3 raised to the power 5, and so on? Should I dissect the problem? The answer is yes. But what would I actually get out of it? 1 raised to the power 5. 1 has the cyclicity of 1, because 1 when multiplied with itself is always going to give a unit digit of 1. If I go for 2, 2 raised to the power 5, if it might be difficult for you, I would go with this formula. Exponent divided by 4 would give me a remainder of 1. Then 2 raised to the power 1 gives me the unit digit as 2. Similarly, with 3, similarly, with 3, I'm going to have a cyclicity of 4. So 3 raised to the power 5, the unit digit, the remainder is going to be 1. So the unit digit is going to be that of 1, 3. So what we have over here is, we have, instead of going with the power of 5, we can find out the unit digit of 1 plus 2 plus 3 till that of 20, till that of 20, and call it the unit digit of this entire equation. This is definitely possible. When this sort of thing is definitely possible, what we actually go ahead and do, we need to find out the sum for 1 till 20. I'll use the simple summation formula of 20, simple summation formula of arithmetic progressions, n by 2 in the bracket 2 times a, which is 1, plus n minus 1 means 19, into d is equal to 1. What I'll get out of it is 20 divided by 2 multiplied by, this is 2 plus 19 is 21, and this gives me an answer of 210. This gives me an answer of 210. So from here I can easily say that the unit digit, is equal to 0. Okay, so we did not calculate the power of 5 for each and every number. I could see a pattern that had I even gone to 20 raised to the power 5, I would have to divide the exponent by 4, would have gotten the same remainder as 1, and would have assumed that 20 raised to the power 1, which is also equal to 20, is going to be my final unit number. Okay, so at times you have to see multiple patterns so as to quickly reach your answer. Okay, I hope this is good. There is another way of calculating, the sum of digits or the sum of numbers which come in a series. I can see this is a plain series, so the formula is n into n plus 1. Okay, n into n plus 1 whole upon 2. We could have reached this point a little early, but I used the concept of AP, or the sum of APs. The sum of APs, is equal to n by 2 in the bracket 2a plus n minus 1 multiplied by d. A being the first digit or the first number, n being the total number of total number of terms in the series, and d being the common difference. Okay, I hope we are good to go. What is the unit digit in this entire case? Whenever you encounter such a case, you need not multiply 3 with entire 38 or 38 entirely with 357. What you can do is, you can again cherry pick the unit digits and multiply them. Okay, you can again cherry pick the unit digits and multiply them. The unit digit of 3 is 3, the unit digit of 38 is 8, the unit digit of 357 is 7, and the unit digit of 1 2 5 6 is nothing but 6. I hope it is easy for all of you to multiply these four numbers. If not, I still have a hack for you. 3 multiplied by 8 gives you 24. I'll use a unit digit. 7 multiplied by 6 gives me 42. I'll use a unit digit. 4 multiplied by 2 gives me an 8. And this is the final unit digit which you had to reach. Imagine a question looking this complex can be solved with so much of ease. By using the branched method. I'm just calling it a branch method. It is not a standard method, but only thing that we are supposed to focus on is the unit digits can be multiplied so as to reach the unit digit of the entire operation. Okay, the multiplication we have over here is the operation that we are focusing on. Moving ahead. Now, I think we've done the question, haven't we? Yes, I think we've done the question. Here it is. 164, 169, 333, 737, 727, 726. Yep, we've done the question already. there is this new concept which I'll be talking about, sum of factors, in a while. Yeah. So now we are at the concept number 3, number systems. And the concept number 3 talks about to find out the number of factors. The number of factors or the sum of factors. I'll take a very small example and tell you what I actually mean by all of this. Let's say I have the number 6. There are 4 factors of 6, and the 4 factors of 6 are 1, 2, 3, and 6. So this number is pretty small for me right now. It's only 6. Had it been, let's say, 7,280, then for you to find out the factors would have been just a little tedious process. And the question won't come that tell me all the factors of 6 or tell me all the factors of 7280. The questions which can be expected in the examination are tell me the number of factors of 6 or tell me the number of factors of 7280. Tell me the sum of factors of 6 or sum of the factors of 7280. So in this situation, what we would do? First of all, 6 needs to be prime factorized. In prime factorization, 6 is made out of 2 and 3, 2 multiplied by 3. So the power of 2 which is used is 1 and the power of 3 which is used is 1. So if I need to find out the sum of factors or like the number of factors first, so what I'll have to do is I'll use this one and I'll use this one. This one corresponds to the factor, the power of 2, and this one corresponds to the power of 3. So 1 plus 1 would be multiplied by another 1 plus 1, which would give me the answer as 4. And my number of factors would be equal to 4. Are we clear with that? Okay, this is 1, 2, 3, and 4. We have 4 factors of 6. I hope the concept of number of factors is clear. Then, talking about the sum of factors. Again, we'll use the prime factorization method. I have factored it down to 2 and 3. Both the powers of 2 and 3 are 1 and 1. So what I'll do now is, I'll start from the power of 0, 2 raised to the power 0 plus 2 raised to the power 1 multiplied by 3 raised to the power 0 plus 3 raised to the power 1. This would give me the output as 1 plus 2 multiplied by 1 plus 3. So this is 3 multiplied by 4, which is equal to 12. And if I add all of them up, 6 plus 6, this also makes it 12. So I have an output out of it, right? Output out of it now. What is the output say? When there is a number n and you need to find out the number of factors, the first thing that has to be done that it needs to be factored into its prime factors. Okay, a raised to the power p multiplied by b raised to the power q multiplied by c raised to the power r and so on. If you need to find out the number of factors, the number of factors would be found out with p plus 1 multiplied by q plus 1 multiplied by r plus 1 and so on. Okay, whatever is the power of the prime factors, you need to add 1 to them and multiply them together. If you need to find out sum of all the factors, okay, if you need to, this exercise was for number of factors. If you need to find out the sum of the factors in this particular case, what you're supposed to do is a would be taken to the power 0 plus a to the power 1 plus a to the power 2 plus so on till a raised to the power p. It would be multiplied by b raised to the power 0 plus b raised to the power 1 plus b raised to the power 2 and so on till b raised to the power q multiplied by c raised to the power 0 plus c raised to the power 1 plus c raised to the power 2 plus so on till c raised to the power r. Okay, till c raised to the power r and so on. This would be my sum of the factors. Okay, sum of factors. Now there is a possibility that it would ask you the number of even factors or odd factors. If you need to find out the even factors, let's assume the first factor which we catch hold of is usually 2. For any even number, the first factor that we always catch hold of is 2, and we are considering that a here refers to 2 being the smallest factor. Okay, so whenever you're supposed to find out odd factors, whenever you're supposed to find out odd factors, at that time you have to deliberately miss out on p. You don't have to count things starting with p. So I will directly start with q plus 1 multiplied by r plus 1, and so on. Q plus 1, r plus 1, and so on. If I'm talking about even factors, if I'm talking about even factors, at that time I have to consider p in the equation, but not with a plus 1. Okay, I have to I have to calculate, or I have to consider p in the equation, but not p plus 1. Okay, that is why when you add both these equations up, you would automatically get a p plus 1. That's why you need not consider a p plus 1 in the even terms. Okay, p multiplied by q plus 1 multiplied by r plus 1, and so on. So number of even factors are calculated in this order and in this factor. Now if I wish to find out sum of all odd factors, I have already calculated sum of factors. Now if I talk about sum of even or odd factors, sum of even or odd factors. So for the sum of all odd factors, for the sum of all odd factors, I will have to consider that a, or the first two which is available there, a to the power 0 is already there. Or simply, I won't be considering it because anything to the power 0 is equal to 1. Okay, anything to the power 0 is equal to 1. Now it will be multiplied with b raised to the power 0 plus b raised to the power 1 plus b raised to the power q. Okay, it will go on till q. Similarly, c raised to the power 0 plus c raised to the power 1 plus c raised to the power r, because it will go till r. It will go till r. So whenever I am considering the sum of even or odd factors, let's assume we are talking about odd factors over here. At that time, we would not consider the prime factor or its power of 2. Okay, no even factor would be used. Moving ahead to sum of even factors. At that time, a raised to the power 0 will not be used. It would start from a raised to the power 1, then a raised to the power 2, going on till a raised to the power t, multiplied by b raised to the power 0 plus b raised to the power 1 plus b raised to the power q. Similarly, it would go on till c raised to the power r as well. Okay, so I have discussed four main areas over here. Okay, I have discussed four main areas over here. The first one being how to calculate the number of factors. If the first step that you'll be taking is to split everything into the most basic prime factors, put an exponent to it, put an exponent to each of the factors, then add a plus 1, add a plus 1 to all the exponential powers. That will give you the number of factors. If you use this sort of an equation where you put the prime factor to a power starting from 0 till p, or till the power it was already with, so that way you will get the sum of the factors. For number of even or odd factors, you have to consider p, you don't have to consider p. Okay, for sum of even or odd factors, you have to consider a raised to the power 0, or you don't have to consider it and start from a raised to the power 1. I hope I've made myself very, very clear about it. Okay, so moving to the first question. Find the total number of factors of 400. Find the total number of factors of 400. I need to put it to prime factorization first. 400 has to be split. Now, 2 raised to the power 2 will make 4. We need another 2 as well, or another 4 as well, because 4 into 25 is equal to 100. Okay, 4 into 25 is 100. This is equal to 100, and now 2 multiplied by 2. I'll now change it to prime factors with powers. 2, 1, 2, 3 and 4. So 2 raised to the power 4 multiplied by 5 raised to the power 2. Okay. Now we've created 400 out of this prime factors. Out of these prime factors. Moving ahead, I already have the prime factors available with me. So the total number of factors, as I've already said, the total number of factors would be equal to p plus 1, the power plus 1 multiplied by q plus 1, and so on. We have two prime factors, 2 and 5. So 4 plus 1 and the power 2 plus 1. Are we good? 4 plus 1 is 5, 2 plus 1 is 3, 5 plus 3 is, 5 multiplied by 3. This is nothing but 15. Okay, so we have the output. The total number of factors of 400 are 15. Moving on, find the total number of odd factors. Find the total number of odd factors. The total number of odd factors of 720 need to be found out. Now 720, this is 8 9s are 72. Okay, so I can split it into 8 multiplied by 10, 80. Okay, and 9 over here. 9 is nothing but 3 raised to the power 2. We already have 2 raised to the power 4 over here, because 8 into 2 is 16 and 16 is 2 raised to the power 4 multiplied by 5 raised to the power 1. Now I need to consider only and only odd factors. I need to consider only and only odd factors. So I won't the number of odd factors. So I won't be considering the exponent of 2, which is equal to 4. I won't be considering this. I would only be multiplying 2 plus 1. These are the exponents of 3. Okay, putting it in a bracket, multiplied by 1 plus 1. These are the exponents of 5. So 3 into 2, which is equal to 6. And this would be my final response. All right, I think we are good to go. I think we are good to go. Moving ahead to the next question. Find the total number of even factors of 4200. Okay, I need to find out the total number of even factors of 4200. What happens with 4200 is, I'll quickly put it down to a point where I can find out the prime factors. 7 into 2 into 3, that is 7 into 6 is 42. 4 multiplied by 25 is 100. Out of these two, I get that the power of 2 was used 3 times, and the power of 3 was used once, the power of 7 was used once, and the power of 5 was used twice. Okay, the power of 5 was used twice. So I need to find out only the even factors. So the power of 2, or the power of the most basic even factor, which is 2, would be used up directly. There won't be a plus 1 attached to it. Okay, 3 multiplied by 1 plus 1 multiplied by 1 plus 1 multiplied by 2 plus 1. I hope you're able to understand that the first one is the exponent of the power 3, and the second one is the exponent of power 7, and the third one is the exponent of power of 5, and the first one 3, which is written over here, is the exponent of power 2. Okay, is the exponent of written power 2. So what I'll do with it is, I'll quickly multiply all of it. 3 2s are 6, 6 2s are 12, 12 3s are 36. So we have 36 as the total number of even factors of 4200. Moving on to the next question. Find the sum of all factors of 520. I'll quickly split it down to its prime factors. 520. 13 fours are 52. Okay. And then another 10. 2 multiplied by 5. So I can say that 2 raised to the power 3 is with me. Multiplied by 13 raised to the power 1 is with me. And multiplied by 5 raised to the power 1. Okay. 2 raised to the power 3. 13 raised to the power 1. And 5 raised to the power 1. So once we have all of it with us, I'll quickly move to my next point. I need to have, I'll take you back to the formula which we used. Okay. The formula of sum of factors was take all the exponents, put them to power in a series from 0 to p, and then multiply all of them. I'll come back here. 2 raised to the power 3 would start from 2 raised to the power 0 plus 2 raised to the power 1 plus 2 raised to the power 2 plus 2 raised to the power 3. Similarly, 13 would start from 0 and go till 13 raised to the power 1. 5 would start from 0 and would go till 5 raised to the power 1. This would give me the answer as 1 plus 2 plus 4 plus 8. This would give me the answer as 13 plus 1. And this would give me the answer as 5 plus 1. Now I need to multiply all of them together. This is equal to 15, this is equal to 14, and this is equal to 6. Right? 15 6 are 90 and 9 14s are 126. So my answer is 1260. My answer is 1260. I hope it is clear to everybody. I hope it is clear to everybody. Moving back to the next question. Sum of the even factors of 520. I need to find out the sum of the even factors of 520. I'll quickly split 520. 13 fours are 52. 13 fours are 52. And 2 into 5 would give me 10. So 2 raised to the power 3. 2 raised to the power 3 multiplied by 5 raised to the power 1 multiplied by 13. Okay. 13 raised to the power 1. For using up the, I need to find out the sum of the even factors this time. Okay. The sum of the even factors. So what I would do is I'll go back to the formula. Yep. I'll go back to the formula. The formula says that 2 raised to the power 3 would not start from 0 but would start from 1. 2 raised to the power 1, 2 raised to the power 2 plus 2 raised to the power 3 whole in the bracket, then multiplied by 5 raised to the power 0 plus 5 raised to the power 1 multiplied by 13 raised to the power 1 plus 13 raised to the power 0 plus 13 raised to the power 1. Okay, I'll go ahead. 2 plus 4 plus 8. Okay, no. Yeah, 2 plus 4 plus 8. This would give me 14 multiplied by 1 plus 5, that would give me 6 multiplied by 1 plus 13, which would give me 14. Okay, so we already have it with us. The square of 14 is nothing but 196, and it would be multiplied by 6. This would give me the answer as 6 6 are 36, 6 9s are 54 57, 6 1s are 6, 1176. So 1176 is my final answer. Okay, 1176 is my final answer. Moving to the next point. I need to find out the sum of the odd factors of 520. Sum of the odd factors of 520. In terms of odd factors, I would not consider the power of 2. Okay, I'll pick up the factors of 520 again from here, which is 2 raised to the power 3, 5 raised to the power 1, and 13 raised to the power 1. So 2 raised to the power 3 into 5 raised to the power 1 into 13 raised to the power 1. 2 raised to the power 3, I won't be using it, so 2 raised to the power 0 is what I'll write over here. 5 raised to the power 0 plus 5 raised to the power 1, 13 raised to the power 0 plus 13 raised to the power 1. 2 raised to the power 0 is 1, 5 plus 1 is 6, 13 raised to the power 0 is 1, and 13 is 13 over here. So this would turn into 14, and this 2 raised to the power 0 would turn back to 1. So this is going to be 84. 84 is my final output. Okay, one more thing. Here we found out the sum of all the factors of 520, right? Here we found out the sum of all the factors of 520. It came out to be 1260. When we're talking about sum of all the even factors, it came out to be 1176. And here the sum of all the odd factors came out to be 84. So we already have, if you add up 1176 and 84, you will get 1260. So this proves that the strategy that we are using is completely fine and we can go ahead with it. Okay, so moving on to the next question. If n is equal to 3 raised to the power 14 plus 3 raised to the power 13 minus 12, then what is the largest prime factor of n? What is the largest prime factor of n? So for this particular thing, I'll try to create n in such a picture where I only have multiples in it. I need not have the operations of plus and minus over here. I need to remove them out of the equation. So what I'll quickly do is I'll take 3 raised to the power 13 common. Okay. When I do that, I'm left with 3 raised to the power 1 plus 1 in common and minus 12. I'll go one step further. 3 raised to the power 13 and 4 would be here. Okay. Minus 12. Again, 3 raised to the power 13. 3 raised to the power 13. If I bring 1 13 out of it, or 1 raised to the power 3 out of it, I would be left with 3 raised to the power 12 multiplied by 12 minus 12. Okay, 3 raised to the power 12 multiplied by 12 minus 12. So here I can take 12 common and it would give me 3 raised to the power 12 minus 1. Okay, it will give me 3 raised to the power 12 minus 1. Now, there's a small logic which I'll be using. The logic says that a cube minus b cube is equal to a minus b multiplied by a square plus b square plus ab. Okay, a square plus b square plus ab. This is my game. I'll be using this logic over here. So for that, I would have 12 again over here. 3 raised to the power 4 multiplied by 3 multiplied by 3. Yeah, and minus 1. And I can put any power on 1. That is why I'll put the power of 3 on 1. Okay, moving ahead one more time. 12 would now be multiplied with 3 raised to the power 4 minus 1. And further, it will be multiplied by 3 raised to the power 8 plus 1 plus 3 raised to the power 4. Okay, so this would give me 3 raised to the power 4 is 81. 3 raised to the power 4 is 81. So 12 multiplied by 81 minus 1 is 80. Then 3 raised to the power 8 plus 3 raised to the power 4 plus 1. Okay. You can do it on your own as well, but I have done it on my own first. So the output of this is 6643. The output of this is 6643. I need to find out the largest prime factor, so I will have to further divide 80 into its pieces and 6643 into its pieces. When I try to divide down 6643 into its pieces, what I get is 12 multiplied by 80 multiplied by 91 and multiplied by 73. Okay, so 91 isn't a prime number, but 73 is definitely a prime number. So the largest prime factor of n is nothing but 73. Okay, this was a little complicated, but I have managed to give you the best output out of it. Okay, this identity is the cube's identity, which you will be learning further. But for now, you might be knowing a little bit of it, and this was what came into play. Right? Moving on. Find the number of prime factors in the product. Find the number of prime factors in the product. What I'll do is I'll further break them down. I'll further break them down and create the output of it. Okay, number of prime factors. Whatever we were doing over here, I'll take you back over here. Here we were trying to find out the number of factors. Okay, we were trying to find out the number of factors. When we were finding out the number of factors, all the factors were being brought into consideration. 1, 2, 3 and 4. Out of all these 4, there is a factor which is itself. There is a factor which is itself, and it was also getting counted. And this is not a prime factor. Okay, this is not a prime factor. So this was also getting counted. But in the question that we're talking about right now, we need to find out only the prime factors. We need to find out only the prime factors. When such a situation arises that you have to find out only the prime factors at that time, what you would do is P plus 1, Q plus 1 and R plus 1. This would give you all the factors. But when I am talking about only the prime factors at that time, I would multiply P with Q with R. Okay, I would multiply P with Q with R. I hope that is perfectly fine. Okay, I'll quickly bring them down to their prime factors. 3 into 2 into 3 to the 6, 6 5 is a 30. Okay, this is 30 and this is raised to the power 5. Then 24, 6 4s are 24 or 8 3s are 24. 2 raised to the power 3 is 8 and 8 3s are 3 raised to the power 1. This would give me a 24. So 2 raised to the power 5, we already have 2 raised to the power 5 plus 2 raised to the power 15, that would give me 2 raised to the power 20. Similarly, 3 raised to the power 5 plus 3 raised to the power 5, that would give me 3 raised to the power 10. Further, 5 raised to the power 5. 5 raised to the power 5. 5 raised to the power 5. Now, the total number of prime factors, would come out to be right. There's a small silly point which was missed, and that point is basically this. that to find out all the prime factors, you have to use the addition symbol. So the output would be 20. The output would be 20 plus 10 plus 5, which is nothing but 35, and this is my final output. Okay, this is my final output. I think we are good. Yes, we are. Moving ahead. What is the total number of factors in the number 840 except 1 and the number itself? Except 1 and the number itself. So I think I already solved it once, but I'll tell you what I'm talking about over here. Let me quickly break down 840 into its prime factors. Okay, 840 into its prime factors. 7 12s are, and 7 3 into 2, 7 into 3 into 2. This would give me 84 multiplied by 2 into 5. 2 raised to the power 2 multiplied by 5 raised to the power 1 multiplied by 7 raised to the power 1 multiplied by 3 raised to the power 1. Okay, 2 raised to the power 2, 5 raised to the power 1, 7 raised to the power 1, and 3 raised to the power 1. Okay. 7 12 sevens are 84. 12 and 7 3 2s are 6. No, 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 there's another 2 which is required here. This makes it 2 raised to the power 3. Now I'll try to find out sum of all the factors. No, the number of all the factors. The number of all the factors would be 3 plus 1 multiplied by 1 plus 1 multiplied by 1 plus 1 and multiplied by 1 plus 1. This would give me the output as 4 into 2 into 2 into 2. Okay, this is 8 4s are 32. 32. As I already have 32 with me, there is an operation which I need to do. I need to find out the total number of factors except 1 and the number itself. The two factors of 840 would also include 1 and 840. These factors come out to be 2 in number. So my final output would be dependent on 32 minus 2, which is also equal to 30. Okay, which is also equal to 30. And this is my final outcome. This is my final outcome. Moving ahead. Coming down to finding out the number of trailing zeros. The number of trailing zeros. My question to everybody is, how is 0 formed when it is in a composite number? Okay, how do we find the source of 0 in a composite number? Let me figure out a way. The way which I'm going to use is with an example. The example says 20. The number is 20. I need to find out how the 0 was produced. So 4 multiplied by 20. 2 raised to the power 2 multiplied by 5 raised to the power 1. Now I'll try to find out how these two zeros emerged. So this is 4 into 50, or yep, 2 into 4 into 25. 5 raised to the power this 25, 8 is 200. So this way I'll try to find out within 2000. Okay, so this would come out to be 5 raised to the power 3, which is 125, multiplied by 2 raised to the power 3. Now there is an algorithm, or there is a pattern which I can see. Out of the two powers, out of the two powers of 5 and 2, the lower power is equal to the number of zeros, or the number of trailing zeros. I can see it here as well. The lower power of 2 and 5 was with 5, which is equal to 2. So number of zeros are number of trailing zeros are 2. Similarly, the power are equal over here, but the power is 3. So the number of trailing zeros is equal to 3. So what you have to do is you have to break down the number into its prime factors. You have to break down the number into its prime factors and find out the two standard factors, which are that of 2 and 5, and whichever, let's assume this is P, this is Q, and if P is greater than Q, then Q is my answer, and if Q is greater than P, then P is my answer. Okay, okay, P is my answer and Q is my answer. This is how we operate. I hope it is good. Moving ahead, I need to find out the number of trailing zeros in this entire equation. Usually, now I'll give you a shortcut. Usually, the number of 2's are much greater than the number of 5's. This means the power of 2 is usually greater than the power of 5. So I can use a shortcut, and the shortcut says that I just need to quickly calculate the powers of 5 which are available, and as soon as I get them, I'll be able to say what would be the number of zeros in the end. In this equation, we'll go the full way. 6 4s are 24, or 8 3s are 24. 2 raised to the power 3 multiplied by 3 multiplied by 4 5s are 20. 2 raised to the power 2 multiplied by 5, and 50. 5 square multiplied by 2 is 50, and another 5 square. So the total number of powers of 2 is equal to 6. The total number of powers of 5 is equal to 5 raised to the power 5 multiplied by 3 raised to the power 1. As I've already taught you, check out 2 raised to the power 6 and 5 raised to the power 5. Now 5 raised to the power 5 is lesser as compared to 2 raised to the power 6. I'm just um, I'm just comparing the power of 5 and the power of 6. So I'll use the one which has a lesser power, which means the number of trailing zeros would be equal to 5. Out of 2 and 5, whichever is lesser, you will have to use that. And 5 is my answer here. Alright, we are good to go. I need to find out the number. I've already solved it. Okay, I was just checking maybe that time. I need to find out the number of trailing zeros in 8 raised to the in 8 factorial. Okay, in 8 factorial, you just need to find out how many 5s are there. I'll quickly do it. 8 factorial means 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1. Okay, I have the power of 5 only once. So 5 raised to the power 1. The answer is already 1, but I'll still calculate the powers of 2. The power of 2 is 1 here, 2 here, and 3 here. 3 and 6. No, there's another 2 over here in it. Yeah. So 3, no, there's only 1, 2 here. 3, 4, 5, 6, 7. And 2 raised to the power 7. To make 1 0, you need at least 1 5 and at least 1 2. Okay. So 5 raised to the power 1 and 2 raised to the power 7. I only have one 5. So the number of trailing zeros, the number of trailing zeros is equal to 1. Okay. I hope I'm very, very clear with this. Now, concept number 5 talks about divisibility rule. Divisibility test or divisibility rule. The first divisibility is that of 2 raised to the power n. Is that of 2 raised to the power n. What happens in 2 raised to the power n is that whenever a number is supposed to be divided by 2 raised to the power 1 or simply 2, the unit digit should be divisible by 2. Okay, or to simply call a number even, the unit digit is supposed to be even. When I talk about 2 raised to the power 2 or 4, at that time the two digits last two digits last two digits would be divisible by 4. Similarly, 2 raised to the power 3 or 8. Okay, so last three digits are supposed to be divisible by 8. Similarly, 2 raised to the power 4, I hope you're getting a hang of it, which is equal to 16. Last four digits should be divisible by 16. Okay, I have 2, 4, 8 and 16 with me. 2, 4, 8 and 16 with me. This is the test of divisibility for 2 raised to the power n. All right, moving ahead. XY7b is a 4-digit number divisible by 4. What is the largest value of b? As I've already talked about the divisibility test for 4, the last two digits, okay, the last two digits need to be divisible by 4. The last two digits which I have are 7 and b, and this needs to be divisible by 4. I'll quickly run I'll quickly run through the table of 4 in terms of 70s. Okay, I'll divide it by 4, which would give me 4 ones are 4. I'll be left with 3 in carry, and I have 3b with me. Now this 3b is supposed to be divisible by 4. 4 8s are 32. This is 1. 4 8s are 32. So the value of b can be 2, and 4 9s are 36. So the value of b can be 6. Okay, I have two values of b which are satisfying my question of xy7b being xy7b being divisible by 4. I need to find out the largest value of b. So 6 is greater than 2. That is why the largest value of b is nothing but 6. Okay, the largest value of b is nothing but 6. This is how we apply the rule of divisibility by 2. 2 and its powers. Alright, moving to the next question. Now comes the divisibility rule of 3 or 6. Sorry, not 3 or 6. It's basically 3 or 9. 3 or 9. What happens in the divisibility rule of 3 or 9? I'll tell you. For 3, for 3 and for 9. Sum of digits are divisible by 3. For 9, sum of digits divisible by 9. Okay, I'll use a classic example. And I'll use 33 over here. 33, when the sum of the digits is done, it is 6. And 6, when divided by 3, gives a 0 remainder, which means it is divisible by 3. But similarly, when 33, the sum of digits, when it is divided by 9, it gives 6 as remainder. So this is not divisible by 9, and this is divisible by 3. Okay, not divisible by 9 and divisible by 3. So these 2 points are very much standard. These 2 points are very much standard for all the divisibilities of 3 or 9. The sum of the digits are supposed to be divisible accordingly. Okay, the sum of the digits are supposed to be divisible accordingly. Moving to the question, check whether 35721 is divisible by 3 or not. 3 5 7 2 1. I'll quickly check it. 3 divisible, 3 divisible, 7 plus 5 12 divisible. Okay, so the sum of the digits are divisible by 3. Therefore, yes, my answer is a clear yes. What did I do? I quickly found out all the multiples of 3. 3 is here. Now 2 plus 1, 3 is here. And 7 plus 5, 12 is here. So all of them are divisible. Okay. You can find it out separately or simply do 3 plus 5, 8, 8 plus 5, 7, 8 plus 7, 15, 15 plus 2, 17, 17 plus 1, 18, which is again divisible by 3. Okay. I hope we are good. Which of the following is the nearest number to 13051 and is divisible by 9? Now, I need to find out the sum of the digits first. 3 plus 1, 4. 4 plus 5 is 9. 9 plus 1 is 10. The sum of the digits is 10. Okay. This is a summation sign. This sign is called summation. This sign is called summation. So, summation 10 is my sum of all the digits. Now I need it to be divisible by 9. As I've already talked about over here, sum of digits are supposed to be divisible by 9. What number comes very close to what number comes very close to 10, which is also a divisible of 9, and we cannot go lower? The reason to that is we don't find any number over here which is less than 13051. All the numbers are in positive light only. So what I'm going to do is I'll read out the table of 9. 9 ones are 9, 9 twos are 18. 9 ones are 9, 9 twos are 18. I'll quickly do is 10. I already have 10 with me. So 10 plus 8. This gives me 18, and 18 is divisible by 9. So I'll add the same 8 over here in my equation, and the output would be 13059, which would in turn be divisible to 9, would be divisible by 9. And this is my final answer. Got it? Got it? Moving ahead. Now, concept 7 talks about divisibility. Divisibility by 11. divisibility by 11. In the concept of divisibility by 11, what happens is, let's assume I have a number A, B, C, D, E. Okay, I have a 6-digit number A, B, C, D, E. In this 6-digit number, I need to find out if it is divisible by 11 or not. What I would do is, I would find out the alternate terms. Okay, I'll find out the alternate terms and then find a difference between them. A plus C plus E, I would find a difference between them, minus B plus D. This is not a 6-digit number, this is a 5-digit number. Let me use an F over here as well. Okay, this is the fifth one, B plus D plus F. Now, now A plus B plus C minus B plus D plus F. Now the difference between the two should be equal to 0 or should be divisible by 11. Okay, should be divisible by 11, or it can be 0, 11 or any factor of 11. That is when a number can be divided by 11. Okay, that is how a number can be divided by 11. I'll move quickly to the question. 14641 is divisible by 11 or not? Okay, 14641 is divisible by 11 or not? I'll quickly put them here. 14641. I'll pick the alternate numbers 6, 7 and 8. 6 plus 1 plus 1 subtracted by 4 plus 4. 6 plus 7 plus 8. 8 minus 8, it would give me 0. 8 minus 8 would give me 0. This means that 14641 is divisible by 11. I've already talked about the property over here that the alternate ones need to be added up and they need to be subtracted. Okay, the alternate ones need to be added up and subtracted. All right, good enough. Moving ahead. Which of the following numbers is not divisible by 11? Okay, I'll quickly do it. 1 plus 3, 4. 4 plus 6 is 10. 10 plus 6 is 14. 7 plus 5 is 12. 12 plus 2 is 14. 14 minus 14, 0. This is divisible by 11. 7 plus 2, 9. 9 plus 6 is 15. I have 15 over here. 5 plus 5 is 10. 10 plus 3 is 13. 13. Okay, so the remainder is 0. This is not divisible. I already have my answer with me. So 1 plus 6 is 7. 7 plus 3 is 10. 10 plus 8 is 18. 18, then 6 plus 1 is 7. 7 plus 1 is 7 plus 0 is 7. 18 minus 7, I have 11. This is again divisible by 11. 1 plus 0. 0 plus 5 is 6. 6 plus 9 is 15. 15 minus 9 plus 4 is 13. 13 plus 2 is 15. This is also 0. So this is divisible. So my clear answer is 752563. 752563 is not divisible by 11. Okay, it is not divisible by 11. All right, now, so we are at concept number 8. In concept number 8, there is something that I'd like to tell you. We've learned most of the prime numbers, mostly 2 raised to the power n. Then 2 raised to the power n accounts for all the numbers which are divisible by 2, or all the numbers which come in with the exponents of 2. So 2, 4, 8, 16. Okay, so such numbers are already covered. Then we talked about the most important thing, which was 3. 3 was very vital because sum of the digits was involved. Then we also talked about 9, where again the sum of digits was involved. But against 3, the division was supposed to be like the sum of the digits was supposed to be divisible by 3. Similarly, for 9, the sum of digits was supposed to be divisible by 9. So, as we've already fixed a firm foundation, there are a few numbers which I would like you to know about. They are 5, 0. Then the couple we've already learned 11. Okay, we've also learned 11, where we are alternating sums. Okay, we are alternating sums or alternating differences. I should rather say alternating differences. We'll check the alternate differences and come to a conclusion. So I have I think 1, 2, 3, 4, and 5. Five types of like 5 times of prime factors factorization, which is left, where we have to find out remainders when, or when we are just supposed to check if the number is divisible by 5, by 7, or by a triplet of 3, 7, 11, or a triplet of 7, 11, and 13, or compounds as well. Okay, I'll tell you what they actually mean. When we talk about the divisibility of 5, the only thing that we need to check is the unit digit. Okay, we need to check the unit digit, and the unit digit can either be 0 or be 5. Okay, the unit digit can either be 0 or be 5. When the unit digit is either 0 or 5, then the number is divisible by 5. Okay, this is a very clear picture. Let's assume the number is 105095. Okay, just because it has 5 in the end, I can easily say it is divisible by 5. Similarly, 98720, again, when it is divisible divided by 5, you can easily see that the last unit digit is 0, and here the unit digit is 5. Whenever you find such a case, we can most assuredly say that it is divisible by 5. Okay, coming down to the second point, coming down to the second option. The second option talks about the divisibility by 7. In divisibility by 7, trust me, it is easier. It is easier. It is easier to check manually. But as people really want to have rules and really love to have rules, then I'll tell you how it actually works. A, B, C, D, E, F. If such a big number is supposed to be checked for divisibility by 7, what we do is I pick up A, B, and C together, and I club D, E, and F together. Let's say the number is bigger than this as well. A, B, C, D, E, F, G, H, I, J, K, and L. Okay, so G, H, I is here, J, K, and L is here. Okay, let's assume this is a 12-digit number, and we have been given a task to check if it is divisible by 7. So what do we actually do? What we actually do is we take the alternate pairs 1, 2, 3, 4. Alternate triplets, we take alternate triplets. We add together 1 and 3, and we add together 2 and 4. Then we take a difference of them. Then we take a difference of them. After taking a difference of them, if that difference is divisible by 7, that is when we can most assuredly declare that the number is divisible by 7. But trust me, for shorter questions, it is much easier to check manually if it is divisible by 7 or not. All right, I hope we are through with this. Moving on to the next point. Moving on to the next point. What does it mean when I am talking about a divisibility by 3, 7, and 11? It has been seen multiple times that SSC asks that when 3, 7, and 11 are multiplied, what do we actually get? We get 33 multiplied by 7, which is nothing but 231. So it directly asks you if the number is divisible by 231. So instead of fearing the number a lot, it's better you split it. It's better you split the number into 3, 7, and 11. All right, it's much better to split the number between among 3, 7, and 11. So this particular number 231 needs to be remembered as a multiple of 3, 7, and 11. The prime factors of 3 of 231 are 3, 7, and 11. All right, I'm through with this point as well. Coming to the fourth point here. The fourth one is 7, 11, and 13. When we talk about 7, 11, and 13, there is a very unique thing which I see. Okay, I'll ask you to multiply 7, 11, and 13 along with me. 11 into 13 is 143. 143 into 7 needs to be found out. It comes out to be 7 3s are 21, 2 in carry, 7 4s are 28, 3 in 2 in carry. Okay, like 3 in carry now. 7 4s are 7 3s are 21. Just a second. 7 3s are 21, 7 4s are 28, 2 in carry 3, 7 1s are 7, 100. So this comes out to be 1001. 1001. You would ask me, this is nothing. This is nothing but a palindrome. What does a palindrome mean? A palindrome means that when I write the word Nitin and I flip it around and I flip it around, it would become Nitin again. So similarly, when I flip around 1001, it would come out to be 1001. But there is a very unique property. There is a very unique property. What is that unique property of 1001? The unique property is when 1001 is multiplied by a three digit number. Let's assume the number is ABC. Then the output comes out to be ABC, ABC 2 times. Okay, the number comes out to be ABC, ABC 2 times. So this is the unique property. And every time you see 1001 into the equation, you have to remember this. This is a very smart rote learning point which you must understand, that 7, 11, and 13 make up 1001, which in turn, whenever multiplied with a 3-digit number, gives out the output as ABC, ABC. Okay, the output as ABC, ABC. I hope we are good with this. All right. Yeah, one last point. One last point is compounds. Okay, I'll explain compounds here itself. Whenever a number is given, let's assume the number 72 is given. Now, 72 is not made up of 72 is not a prime number alone. It is made up of prime numbers, but 72 is not a prime number alone. So if 72 has to be checked if something is divisible by 72 or not, then you have to split it into its prime numbers which you know, or into compound numbers which you know. So whenever you have to check if a number is divisible by 72, you can split it into 9 and 8. We know the rule of 9, last three digits, and we know the rule of 8, that is last three digits, and we know the rule of 9, that sum should be divisible by 9. The sum should be divisible by 9. Okay, so I hope this concept is clear, that whenever compound question comes, you have to split them apart. And use the minimum factors or the factors which you know about. That I'm very sure that everybody knows about 8, everybody knows about 9. So we'll use big numbers. Okay, not essentially the smallest prime numbers, but numbers of which you know the divisibility rules. Okay, I hope we are good to go. Moving ahead. What is the value of x in the number 342 dash if the number is not is divisible by 6 and not divisible by 5? If the number is divisible by 6 and not divisible by 5. Let's see, if the number is divisible by 6, then there are two numbers it can be broken down into, 3 and 2. 3 and 2. Also, when we are talking about divisibility of 5, the unit digit has to be either 5 or 0. I have both the rules in front of me. 6 is a compound number. The compound number is broken down into its prime factors. Okay, the compound number is broken down into its prime factors. 3 and 2, 5 and 0. So what I'll do is I'll write 342 over here. 342 and x over here. First of all, for 3, I need to check the sum. The sum comes out to be 3 plus 4, 7, 7 plus 2, 9, 9 plus x. When I say 9 plus x, it has to be divided by 3 and divisible by 3. Either, what all possibilities do I have for x if it is supposed to be divisible by 3? Okay, I'm writing 3 over here in double colons because we are working for 3. For 3, for divisibility by 3, the sum is supposed to be divisible by 3. 9 is already divisible, that means x can either be 0, 1 no, 2 no, 3 yes, and 6 yes, and 9 yes. Okay, these are the possible options for x. Further, for 2, I need to check the unit digit. The unit digit, that is x, can be multiple of 2. 2, 4, 6, and 8. Also, I'm again writing it in curly braces. Again talking about 0, sorry, again talking about 5. Let me talk about 5. Let me talk about 5 over here. So, for the divisibility of 5, the unit digit, also, we are talking about not divisible by 5. Okay, so x can cannot be 5 and it cannot be 0. So we have a clear winner with us. We have a clear winner with us. I'll eradicate or I'll eliminate things. Okay, 0 can't be used, 0 gone away. 3 isn't here, so 3 can't be used. 6 is here, 6 is a possibility. 9 is here, 8, and 9 is nowhere else, so 9 is also not a possibility. So from this output, or from this conclusion which I have drawn, I can finally put a name to x, and the name to x is nothing but 6. Okay, because it is fulfilling all the three conditions. It is not getting into the house of 5, it is accommodating the house of 2, and it is also accommodating the house of 3. Okay, so we have 6 as our final answer. I hope you're able to understand what I've taught here. Okay, moving on. As I've already taught, the concept number 9, which you're seeing over here, the concept number 9 talked only about 3, 7, and 11, and also talked about 7, 11, and 13. Okay, it also talked about 7, 11, and 13, 3, 7, 11, and 7, 11, 13. Okay, I hope we're good with it. Moving ahead, which of the following pairs of the non-zero value of p and q make a 6-digit number? It basically meant a 6-digit number, 674, pq 0, divisible by both 3 and 11. Divisible by both 3 and 11. So I'll be employing my weapons of 3 and that of 11. For 3, I need to check the sum. What does the sum say? 6 plus 7 plus 4 plus p plus q plus 0. What does 11 say? 11 says 6 plus 4 plus q when subtracted out of 7 plus p plus 0 is supposed to be either 0 or 11 or a multiple of 11. Or a multiple of 11. So let me quickly gather my horses. 6 plus 7 is 13, 13 plus 4 is 17. Okay, so I have 17 plus p plus q. If I start reading, or if I start simply counting numbers ahead of 17, what do I actually make of it? There's one more important point which I left behind. The p and q are basically non-zero in nature. So I'll start counting for p and q, for the sum of p and q. The sum of p and q can be 1, which is not useful to me because both of them are supposed to be non-zeros. And if I talk about natural numbers are only starting from 1. Whole numbers start from 0. And non-zero is already a limit which has been applied on me. So 1 can't be the answer. 2, no. 3, no. 4, 4, yes. 4, yes, it works. 5, 5, no, it doesn't. 6, no, it doesn't. 7, yes, 7 works. 8, it doesn't. 9, it doesn't. 10, it does work. Okay, I will restrict myself to 10. These are my 4 options available to me. Now I will solve it for, this was the first equation which I solved, and I've brought out I've brought out 3 options with me. Okay, I have 3 options with me. I have three options with me: 4, 7, or 10. Now I'll solve equation number 2 and find out another few options which can be common with 4, 7, or 10. Okay, moving on. 10 plus q minus 7 minus p is either equal to 0 or equal to 11. When I solve this, I get 3 minus p plus q. Okay, and I'm definitely going to put it equal to 0 for a while, and if at all required, I will put it as 11 as well. Okay, so I can easily say that q minus p is equal to 3, or I can easily say, yeah, p minus q. It should be p minus q, it's not q minus p. I should say the difference between p and q is equal to 3. The difference between p and q is equal to 3. This has been very clearly defined. Now I have an equation out of equation number 2. I'll try to focus it on p plus q equal to 4, p plus q equal to 7, or p plus q equal to 10. Okay, let me go ahead and try to figure it out. If these two equations are added up, I get the value of 2q is equal to 7. Okay, this gives me no. The value is 2p. The value of 2p. The value of 2p is equal to 7. That means p is equal to 3.5, and this is not possible. It cannot be a decimal number. It has to be a proper integer. But when I equate p minus q is equal to 3 and p plus q is equal to 7, what I get out of it is 10 is equal to 2p. So the value of p is nothing but 5. When I use this value of p is equal to 5, when I use this value of p is equal to 5, I can get the value of q. I can get the value of q is equal to 2. Okay, I can make the value of q is equal to 2. Which equation did I use to settle this? The equation I used to settle this was p plus q is equal to 7 and p minus q is equal to 3. P plus q is equal to 7 and p minus q is equal to 3. So this was the equation which I used to settle my problem. And once this problem is settled, I will move to the next question. Okay, so if a 9-digit number is divisible by 72, then the value of 4x plus 3y is okay. Now, there is I'll give you a very cute hint over here. I'll give you a very cute hint and see what the hint is. 4 times is multiplied by something and 3 times is multiplied by something, and it is also in the root. If you can remember the triplets, there is a good possibility that whatever comes out here is going to be a multiple of 5. Okay, this is coming right off the bat. I haven't checked it. Let's go and try to clear out this mystery if it is true or not. There is this 9-digit number and it is divisible by 72. So when a number is divisible by 72, I will break it down into two portions which I know of. I don't know the rules of division by 72, but I know the rules of division by 9 and the rules of division by 8. And 9 into 8 is 72. This is nothing but a compound number which is broken down. This is nothing but a compound number which is broken down into multiple parts. Okay, compound number which is broken down into its own parts which I know of. Okay, you can also break it down into 2 and then maybe 36, but you don't know the rules of 36. So it's better to break it down into those areas which the rules you know very well. 9 8s are 72. The rule of 9. What does the rule of 9 talk about? Sum of digits. Sum of digits divisible by 9. Then what about 8? 8 talks about last 3 digits divisible by 8. Okay, it talks about last three digits being divisible by 8. The sum of the the sum of the digits would be divisible by 9 if it is if the entire number is divisible by 9, and the last three digits would be divisible by 8 if the entire number is divisible by 8. So we have to run both of these things in parallel. Okay, so I'll first of all deal with 3, 8 and y. If 3, 8 and y is divisible by 8, then this entire concept turns out to be true. Okay, so 8 4s are 32. 8 4s are 32. We have 6 and y. We have 6 and y. Why do we have 6 and y? Because after dividing 8, after multiplying 8 by 4, we get 32. We get plus 6 as carry. Plus 6 and y together are supposed to be divisible by 8. Okay, so we have 6y upon 8. So I can clearly see that 64 is divisible by 8. So the value of y clearly comes out to be 4. This has been established and we are good to go. Now, talking about the others, I'll use the value of y4 in this one. Okay. So I'll quickly do a sum. 4 plus 6, 10, 18, 18 plus 6 is 24, 24 plus 8 is 32, 32 plus 3 is 35. So 35 plus 4, where is the last plus 4? It's from here, 39. So I have 39 plus x, and this number is now supposed to be divisible by 9. The very next number, which is divisible by 9, and it is right after 39, is 45. Okay, and after that we'll have to have a 2-digit number, but x is a 1-digit number. X is a 1-digit number. So I can clearly see that the value of x is nothing but 6. When I keep the value of x as 6, 39 plus 6 comes out to be 45, and that is what I'm looking for. That is clearly what I'm looking for. So I've gotten the value of x as 6, and I've gotten the value of y as 4. I'll quickly take a root. This is 4 6 are 24 and 3 4s are 12. Okay, I was wrong over here, that I was assuming that the multiple would come out to be 5. So I hope you've learned from my mistake, and the root of 36 is my final answer, which is equal to 6. Good enough? Alright, I'll move on. If the number 55p1067q9 is exactly divisible by 99, then what is the value of p multiplied by q? Okay, I'll quickly break down 99 into its two major components. The major components I see and which I have learnt are 9 and 11. For 9, I would apply the rule of sum of digits. Sum of digits divisible by 9. And for 11, I will do alternating difference. Alternating difference. Okay, alternating difference divisible by 9 by 11. Okay, alternating difference divisible by 11. I'll quickly apply the first equation of 9. Sum of the digits. 55. 5 plus 5 is 10. 10 plus 1 is 11. Then 11 plus 13 is 24. 24 plus 9 is 33. So this is 33 plus p plus q, and this is supposed to be divisible by 9. Mind you that the value of p and q together cannot, like alone cannot be a 2-digit number. So we'll have to maintain it. If we have 33, whatever can be added with p plus q should make it a multiple of 9. So what options do I have? After 33, we have 36. So the value of p and q can be 3. After 36, we have 45. To make it 45, p plus q has to be 12. No, 45, yeah. P plus q has to be 12. Now, to maintain that p plus q doesn't go beyond the single digit that we're talking about, maintaining the point that p plus q doesn't go beyond p plus q that we are talking about, doesn't go beyond a single digit. Okay, we are supposed to keep p plus q in the range below 18. Why have I kept it below 18? Because the p max can be equal to 9 and q max also can be equal to 9. P max can be equal to 9 and q max also can be equal to 9. Okay, so but already I have gotten the value of 12. I have already gotten the value of 12. So I'll move ahead. This is final that p plus q must be equal to p plus q must be equal to 12. This is my first equation. This is my first equation. Now, going one step ahead, going one step ahead, I'll have to check it by 11 now. I'll quickly add up the alternating ones. 5 plus p plus 0 plus 7 is 12. 12 plus 9 is 21. So 21 plus p. Okay, these are the odd digits. Let me check the even digits. Q plus 6 plus 7. 7 plus 5 are 12. So this is 12 plus q. Now this either has to be 0 or has to be equal to 11. Okay, this either has to be 0 or should be equal to 11. I'll quickly solve it for that. This would give me 9 plus p minus q is equal to 0, or I can say that q minus p is equal to 9. Okay, if I already have p plus q as 12 and q minus p as 9, I have assumed this to be 0. Let me quickly try to figure it out with the help of 0 first. When I add this all up, I get the value of 2q as 21 and the value of q comes out to be 10.5, which is a decimal value. Okay, so this is not going to be useful for me. This is not going to be useful for me. Moving ahead, p plus q is equal to 12 is a constant. I will not be changing this, but I can assume that the value of 9 plus p minus q is equal to 11. It can be done, right? It can be done, right? So what I get out of it is that p minus q is equal to 2. P minus q is equal to 2. Through this, I receive that the value of 2p is equal to 14, or the value of p is nothing but equal to 7. The value of p is nothing but equal to 7. So as I've already gotten the value of p, I can plug it in here. I'll just change the pen color. The value of p has been received as 7. I will plug it in here, and which would give me the final output as the value of q equal to 5. What has been asked here? 7 multiplied by 5 has been asked here, which I've just found out. So the value is 35. Okay, the value is 35. Sorted. Moving on. If 6-digit sum, if 6-digit number 5x2y6z is divisible by 7, 11 and 13, then the value of x minus y plus 3z is equal to what? I told you, I told you in the past that whenever you encounter 7, 11 and 13 together, just quickly remember that there is a number 1001. How did it come? This originated because 7 into 11 into 13 is equal to 1001. Okay, 7 into 11 into 13 is 1001. As I already have 1001. I should know that when ABC is multiplied by 1001, I get the output to be ABC, ABC. Or let's say if I have 100 multiplied by 279, the output the output that I would get is 279 and 279. Okay, 279 and 279. This is the output that I would get. Okay, I hope I'm doing good. Yep. So move on. I'll move ahead. The question says that 5x 2y 6z is the number that I have with me. Accordingly, it can be said that 5x2 is equal to y6z. These numbers are the same numbers or the exact same numbers. Okay, these numbers are the exact same numbers. From this equation, I can derive that the value of x is 6, the value of y is 5, and the value of z is equal to 2. The value of z is equal to 2. Okay, so 6 is the value of y. I'll quickly use this equation and put the values here. The value of x minus y plus 3z. X is 6 minus y. Okay, I'll just quickly use it. 6 minus y is 5 plus 3z. 3 has to be multiplied by 2. 3 has to be multiplied by 2. So 6 minus 5 plus 6 is nothing but 12 minus 5, which is equal to 7. Okay, so my final answer comes out to be 7. Good enough? I'll move on. If a 10-digit number is divisible by 72, then what is the value of 5x minus 3y for the least value of y? For the least value of y, you will encounter similar questions where you would be said that what is the least value of x, what is the least value of y for a particular equation. So do not be afraid, just stick to the basics. For 72, I'll do my favorite split again. The split says 8 nines are 72. The split says 8 nines are 72. So what I have over here is the divisibility rule for 8 is 3 digits, the last 3 digits. Okay, the last 3 digits. And for the divisibility of 9, the sum is divisible by 9. Okay, so we are clear about it. We are very clear about it. I'll quickly follow up. 547 26x 79y 6 79y 6. This is the rule for divisibility by. Now I'll quickly use the rules. The rule says the last 3 digits. 9y6 when divisible by 8. Okay, I'll use it. 8 ones are 8. I have 1. With 1 in the table of 8, I only and only get 16. That is divisible. If I use 16, would my number complete out to become 9 by 6 to be divisible by 8? The answer is no. I'll tell you why. I will have to increase this value. I'll tell you why. Because if it is 9 by 600 divided by 8, I studied the table of 8. 8 ones are 8. 8 ones are 8. 1 is carry. I have 1y. If this comes out to be 6, it will be completely divisible. But the 6 in the end would be hanging behind. So I would do a plus 1 and I would make it 7. Okay. So if it is 17, it would go on 8 to the 16, 1 extra, and 1 6 would again be divisible by 8. So the value of y in this transaction comes out to be 7. This has now been established that the value of y is 7, and it is the least value I can actually have. Or should we figure out a different way? Just let me check. If I put the value of y as what? 2? No. What if I put the I have 1 in the remainder. I have 1 in the remainder. The value has to be 6 or more. It can't be less than 6. So I'm establishing the value of y to be 7. Moving ahead, now I have to check it for 9. I'll quickly do the digit sum. 9, 9, 18, 18 plus 6, 24. 18 plus 6 is 24. 24 plus 7 is 31. 31 plus 9 is 40. 40 plus 6 is 46. 46 plus 7 is 47 plus x. 47 plus x. Now this question has to be solved in this manner. This has to be divisible by 9. Okay, this has to be divisible by 9. So 47 plus x should be divisible by 9. The next number which comes after 47, which might be divisible by 9, is nothing but 54. So the value of x that I can derive here is 7. Okay, the value of x that I can derive here is 7. I've gotten the value of x as 7. I've gotten the value of y as 7. I'll quickly do the math. 5x minus 3y, 5x minus 3y is equal to 5 into 7 minus 3 into 7, which would give me the output as 2 into 7, which is equal to 14. Okay, the answer is 2 into 7, which is equal to 14. Okay, so I'll move on. I need to find out what this number is divisible by. For that, I can see a very clear pattern. 2 raised to the power 25 can be taken out as common. 2 raised to the power 25 can be taken as common. Whenever that happens, I would take this as 1 plus 2 raised to the power 1 plus 27. I have 27 over here. So 2 raised to the power 2. 2 raised to the power 2. 2 raised to the power 25 is something which I have. I would quickly solve this bracket. 1 plus 2 plus 4. This gives me an output of 2 raised to the power 25 multiplied by 4 plus 2 is 6. 6 plus 1 is 7. So I can easily say that the special number which this question is looking for is nothing but 7. Okay, it's nothing but 7. Cool enough. I'll move on. Which of the following numbers is divisible by 120? I'll quickly break down 120 to my benefit. I'll break down 120 to my benefit. What does the benefit talk about? It is divisible by 10, it is divisible by 4, and it is divisible by 3. For the divisibility by 10, I'm supposed to simply knock off the unit digit. I'm supposed to simply knock off the unit digit, which is 0. So it will go away. It will go away. So the next step is division by 4. The next step is division by 4. For a division by 4, the last 2 digits are supposed to be divisible by 4. I'll quickly check it. 28 divisible by 4, 24 divisible by 4, 20 divisible by 4, 36 again divisible by 4. So this seems to be a very tough question. But let's not jump to conclusions so early. Let's not jump to conclusions so early. I have 3 here with me and it will definitely come to my rescue. For 3, I need to check the sum of digits. I'll quickly check the sum of the digits. What are the sum of the digits? 7 plus 2 is 9 and 9 and 9. This is 9. So sum of the digits is divisible. So this is divisible. 4 plus 2, 6. 6 plus 5, 11. Not divisible. There's 1, 6. There's another 6, 12. There's another 2. Not divisible. There's 7. There's 3, 10. And there is 17. Okay. So this is not divisible. This is definitely not divisible. So we are very, very clear about it of what is going on. I have 120 here. I have 120 here. So I have come to the conclusion that 10280 is divisible by 120. Okay. For 10, you have to remove the last digit. The last digit is supposed to be 0. Then only it is possible. For 4, the last 2 digits need to be divisible by 4. And for 3, the sum of the digits should be divisible by 3. Okay. I think I've met all the criterions and I'm good enough to go ahead. Okay. There's concept number 10. What does concept number 10 actually do? I'll tell you very clearly what it actually does. In concept number 10, we are going to talk about Venn diagrams. Venn diagrams are nothing but graphical representations. Okay. Venn diagrams are nothing but graphical representations. What kind of graphical representations are they? In which these circles represent quantities. These circles represent quantities, and the empty area represents exclusion. Exclusion. And and the common area that we have talks about inclusion. Talks about inclusion or the common area. Okay. I'll give you a very small example. This is a Venn diagram which I'm creating for students who love maths and for the students who love sciences. Okay. This is maths. This is science. Maths versus science. So I have maths versus science. Now, this is the common area. Let's assume the number of students who like maths are equal to 20 and the number of students who like science is 30. Okay. And the number of students who like both is equal to 5. So when somebody asks me, what is the total number of students who like maths and science? MUS. Okay. Maths and science. This is the symbol of union. This is the symbol of union. If you would straight away tell me that the total number of students who like maths and science together is equal to 30 plus 20 and you'd give me the answer 50, this would be a wrong answer. Okay? This would be a wrong answer. I'll tell you why. Because maths is represented by a Venn diagram which is here on the left hand side. Okay? And science in a perfectly parallel way is represented by a diagram which is here on the right hand side. If you see, if you see just a little more clearly, you would realize that there is a common area. There is a common area where both math and science is liked. Okay? Both maths plus science is liked. This is the area where such a situation occurs. Both maths and science is liked. So just try to understand where we are. Try to understand where we are. Maths and science is liked together. So this area is being double counted here. In this situation, this area is being double counted. To avoid such a situation, to avoid such a situation, to avoid such a situation, I have to exclude it once. I have to exclude it once. So what I would do is I would say 30 plus 20 minus 5. This minus 5 is the common area, is the common area which was being counted twice. So the final value comes out to be 45. Okay. So this is the entire concept of Venn diagrams. There's a small formula which I believe you all should know. The total of A union B is equal to the total of A plus the total of B and minus the total of A intersection B. What does this sign say? This is an inverted U sign. This is called an intersection sign. This is an intersection sign. What does the intersection sign say? That whatever is common, it has to be removed out once. Okay? It has to be removed out once. Now, this thing is a matter of concern that you have to remove it out once. Got it? You have to remove it out once. Moving on. How many numbers are there from 500 to 600, including both, which are neither divisible? This is not divided. This is divisible. Divisible by 3 nor by 7. Okay. So we have to check for 3. We have to check for 7. And we have to check for 21 as well. Okay. We have to check for 21 as well. And after 3 and 7, we would have to exclude. We will have to exclude 21 because that would be called in for double counting. Okay. That would be called in for double counting. That would be called in for double counting. Okay. Just give me 10 seconds. Yep. So there's a thing that I need to check now. For 500, I would have to apply this rule. And for 600 as well, I would have to apply this rule. Then I would have to check what are the total number of numbers which are lying between 600 and 500. That I will have to subtract from that. Let's say that is the number is x. From that number x, I would have to subtract all the outputs which I have received from here. Okay. From that, I would subtract all the outputs that I have received from here. So I'll talk about 600 first. I'll talk about 600 first. We'll talk about 3, which is 3, 7, and 21. 3, 7, and 21. For 3, what would I do is, I would say 600 divided by 3, which is equal to 200. Then I would divide it by 7. I would divide it by 7. 600 divided by 7. 7 8s are 56. 7 8s are 56, another 40. 7 5s are 35. Then I would check by 21. 600 divided by 21. 21 2s are 42. I have 18, 180. 21 8s are 8s are okay. 21 8s are 21 2s are and 21 8s are. This is the output for 600. I would do the same thing for 500. I would do the same thing for 500. For 500, it's going to be 3, 7, and 21. 3, 7, and 21. I have 500 over here. I will divide it by 3. The output would be 166. For 7, 7 sevens are 49. 1 0, 1 0 is 10. 7 ones are 7. Then I have 21. 500 divided by 21. 21 twos are 42. Another 80. 21 threes are 63, which is much less than 80. Okay. So I have this entire output available with me right now. Now, as we already have everything that we require, the output of this entire situation is nothing but 200 plus 85 minus 28. Why is the 28 being subtracted? The reason is very clear, that because it is being double counted. once with 7, once with 3, and once with 7. So I have to avoid the double calculation. So I'm subtracting 28 out of this situation. So 285 minus 28, this would give me a 7, and this would give me a 5. So this would give me 257 as my output. Out of this, the final output is 166 plus 71 minus 23. So when 23 is removed from 166, it comes out to be 143, plus 71 has to be added here. This would give me a 4, this would give me an 11, and this would give me a 214. So I have 257 and 214. Now, if it was asked to me that what are the number of terms which are divisible by 3 and 7 between 600 and 700, my final output would have been 257 minus 214. Okay, 257 minus 214, and this output is 3. This output is 3 and 4. So the output is 43. This output is 43. But I need to check they are not supposed to be divisible. So what are the numbers? What are the total numbers between 600 and 500? That is equal to 100. If both the numbers are included, I will have to add a plus 1 to this equation. That would give me 101. I have to subtract the 43 from this because the question says neither. If the question says neither, 101 minus 43. And this is my correct output. Okay, this is 8 and this is 6. So 68 is my correct output. Okay, 68 is the correct output. I know you would be enticed to quickly calculate the numbers between 500 and 600 and then come to a conclusion if they are divisible by 7 or 3 or not. But trust me, this entire operation which I have conducted in front of you, this entire operation is the most standard thing which has to be done. Okay, let's move on. What percentage of numbers from 101 and 1000 have 9 in the unit digit? Have 9 in the unit digit. So yes, I need to find out what percentage of numbers from 101 to 1000 have 9 in the unit digit. When I say 9 in the unit digit, I mean by 9, 19, 29 and so on. But here there is a catch. The catch says that the numbers would have to start from 101. So the first number that I would encounter would be 109, 119, 129, 139, 149, 159, 169, 179, 189. Okay, so these are 4 and another 4 and 209. Okay, so these are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So in till up to 209, we have 10. We are going to have 10 such instances because we have to go till 1000. So that is why the answer that is why the answer would be 10 multiplied by 10, which is equal to 100. Okay, so they are going to be 100 such numbers which would have 9 in the unit digit. So once that is said, I need to calculate what are the total numbers between 1000 and 101. Okay, between 1000 and 101, the total numbers are going to be 899. But I have to include 101, so I'm going to add 1 to it, which would give me the answer as 900. So the percentage has been asked. When such a question arrives where percentage has been asked, 100 would be divided by 900 and it will be multiplied by 100, and my answer would be what? My answer would be 100 by 9 or 11, 1 by 9%. Okay, so I think we're good enough. Let's move on. How many natural numbers are there which are less than 1000 and are divisible by 5 or 7 but not by 35? by 5 or 7, but not by 35. Let me quickly take you through 5, 7, and 35. Each one of them has to be checked by 1000. I'll check it with 1000. After division, I get the answer as 200. Then, then again by 7. After division, I get the answer as 7 ones are 7, 7 fours are 28, and 7 twos are 14. I get the answer as 42, 142. When 1000 is divided by 35, 1000 is divided by 35, it becomes easier. 5 sevens are 35, 5 twos are 10, and 200. 200 divided by 7. 200 divided by 7. So 7 twos are 14, then I have a 60, 7 eights are 56. I have 26 over here, 28 over here. Now I have these two values. There is a situation, which says yes to 5, it says yes to 7, but no to 35. If I add only these two up, I would get the answer as 342. 342 would be talking about a 5 yes, a 7 yes, and a 35 yes two times. Why is this the case? Why is 35 coming up two times? The reason is pretty simple. I showed you the demonstration through a Venn diagram that when all the numbers divisible by 5 are in this area, all the numbers are divisible by 7 in this area, and this common area would be counted twice. This common area would be counted twice in the union. In the union, this common area would be counted twice. If I remove 35 from it once, if I remove 35 from it once, I would get the answer of divisible by 5 or divisible by 7. But I will have to remove 28. But I will have to remove the value of 35 from this entire equation from 342 twice. And the reason is pretty simple. Because I've already explained, when I'm talking about 5 and 7, 35 is coming twice. Once, which is common, which is legit, and the second time it is coming, it is wrong. So I have to remove the 35 from the equation completely. So what I would do, I would do 35 minus 2 times of 28. Minus 2 times of 28. 2 times of 28 is nothing but 56. 56 when subtracted from here would give me a 14 minus of 300. When the 14 is subtracted out of 300, I would get 286 as my output. So my final answer comes up to be 286. Pretty cool. Moving on. Okay, if the number of items of set A be n of A, n of B, and n intersection A of B is equal to 16, then what is the number of n A union B? If I take you back to this point where I was talking about Venn diagrams, I taught you a certain formula. Which said the total number of terms of A union B is equal to total number of terms of A plus total number of terms of B minus total number of terms between A intersection B. I will be using the same formula. For my rescue over here. The formula says n of A union B is equal to n of A plus n of B minus n of A intersection B. I have the formula. I just need to plug in the values now. N of A union B has to be found out. So 40 minus 26, no, 40 plus 26 minus 16. This gives me the value of what? 30? No, 50. My answer comes out to be 50, and which is correct. All right. So moving on. Number systems concept of 2 unit digits. I think this is coming up. No, this is not the one. Okay. I'll be talking about the most simple thing, which is nothing but LCM. See, the LCM calls out to be the least common multiple between two numbers. Let me take up a number 36 and 96. Okay. We follow the long approach in school where we do this and take down all the prime factors. But this is not the approach that we'll be following. We won't be following this approach. We'll be following a shorter approach for it. What does the shorter approach call for? It calls for 2 multiplied by 3, which is 6, multiplied by 2 multiplied by 3, which is 6. Now I have 6 into 6, which is 36, and 6 into 16 makes my answer. 6 into 16 makes my answer. 6 is already there, but I need a 16 over here. To make a 16, I already have 2. So I just need 2 raised to the power 3 in this equation. So the LCM out of this area would be equal to 2 raised to the power 5 multiplied by 3 raised to the power 2. This is how from now onwards we'll be calculating LCMs. Okay, this is how we'll be calculating LCMs now on. Find the LCM. This is pretty easy. We'll be moving on pretty quickly. Okay, I'll directly be taking 3 square, 9 square, 3 square is 9, 9 3s are 27. Another 3 would be multiplied here. I already have 3 3s. Now this is 9 6 is 54. I already have 9 here, and another 2 would suffice. This makes it 54. Now I need to cater for 12 only. 3 4s are 12. There is not enough space for 4, so I would bring in another 4 over here. Bring in another 2 over here. So I have 4 over here and 3 raised to power 3 multiplied by this. Yeah, so 3 raised to the power 3, 9 3s are 27. 27 into 4. 4 7s are 28, 4 2s are 8, 10. 108 is my LCM of all these three numbers. Cool enough. Moving on. Find the HCF of 18 and 21 by long division. By long division. Okay, so this is a pretty tricky concept. I'll come back to you. The long division method which is required to solve this question is very simple. We have 18 over here and we have another 21 over here. You have to find out, this is the dividend, this is the divider, here we'll get the quotient, and in the end we'll get the remainder. 18 ones are 18. We have 18 over here, we have another 3 over here, and then we have 18. 3 6 are 18, and this comes out to be 0. So the last divisor becomes the HCF, and HCF means the highest common factor. The reason we are see, we could have easily found it out by trying to quickly use a few multiples and a few tables, but we use the long division so as to reach a conclusion with the most accuracy. Okay, so moving ahead, what is the LCM of 15 and 25? Not a difficult question. I'll quickly break it down into 5 and 3. I have to create another 25 out of it, so another 5. So 5 5s are 25, 25 3s are 75, 75 is my answer. Moving ahead, now in this concept we'll be solving the LCM and HCF of fractions. Let's assume these are the following fractions we are talking about. These are the fractions that we are talking about. This is A by B, then there is C by D, and then there is E by F. These three fractions are given, and we are given two operations. One is that of LCM, and the other one is that of HCF. Okay, one is that of LCM, and the other one is that of HCF. When we talk about LCM, whatever we are talking about is supposed to be done in the numerator. So we'll find out the LCM of A, C, and E, and the HCF of B, D, and F. B, D, and F. Further, when we're talking about the HCF, whenever we're talking about the HCF, we will do the same for the numerator side only. I'll follow with HCF for A, C, and E, and the LCM of B, D, and F. Okay, the HCF and the LCM. Whenever such a question comes, when you have fractions involved, whatever is asked, let's assume LCM is asked, so the numerator will be dealt with the same operation. Similarly, when HCF is asked, the numerator will be dealt with the same operations. Moving ahead, find the LCM of 5 by 3, 4 by 7 and 5 by 12. Okay, I'll write them here pretty quickly. 5 by 3, 4 by 7 and 5 by 12. These are three numbers. The LCM needs to be found out. So the LCM of 5, 4 and 5 would be required, and the HCF of 3, 7 and 12 would be required. The LCM of 5, 4 and 5 is nothing but 5 into 4, that is 20, and the HCF of 3, 7 and 12, there is nothing common in them. Two of them being prime and this one being a factor of 12, but 7 is not involved here. So the HCF would come out to be 1. So the LCM of this entire equation is 20 upon 1. Okay, 20 upon 1. So we are good to go. Moving on. Find the HCF of 21 by 5, 12 by 8, and 7 by 12. We are focusing on the HCF. So the numerator would go into HCF. The numerator would go into HCF. HCF of 21 by 12, 21, 12 and 7 whole divided by the LCM of 5, 8 and 12. If I try to find out anything which is common between 21, 12 and 7, I would find out that nothing is common over here. So the HCF would come out to be 1. There is no common factor which I can talk about other than 1. Similarly, in LCM, when I try to talk about that, I have 5, 8 and 12. I'll quickly try to break it down. In 5, 2 into 2 into 2, this is 8, and now 4 into 3, this is 12. 5 2s are 10, and 4 2s are 4 3s are 12. 12 plus 10, sorry, 12 multiplied by 10 is 120. So my output of this question would be 1 divided by 120. My output of this question would be 1 upon 120. All right, we'll move ahead. What is the LCM of these three numbers? Again, we'll convert them quickly into fractions and then solve them. I have 126 upon 1000. We have 36 upon 100. Then we have 96 upon 100. I need to take the LCM of the numerator and the HCF of the denominator. Why? Because in the question it has been clearly mentioned that I need to take the LCM. Okay, so the LCM first and HCF later. So I'll first focus on the HCF. The HCF, or the highest common factor among all of them, is 100. Okay, this is the biggest number which is useful to all the three terms. Then coming down to the LCM, quickly checking 36 and 96. 36 is 6 into 6. 96 is 96 is 12 8 is a 96. Okay, 12 8 is a 96. If I have a 12, I can make a 12 out of this. Then I just need an 8, but I have an extra 2 over here. So 24 4 is also 96. I'll quickly try to bring it down to the most easy terms. I'll start with the biggest number first. I have 126. I'll use a 3. 3 4s are 12. 3 4s are 12 and 3 2s are 6. Okay. So I have 3 into 3 into 2. This would give me a 6. 6 3 is a 18. Now 18 18 8s are, if I'm not wrong, right? No, 18 7s are 126. 18 7s are 126. So I have 3 into 3 into 2 into 7. This gives me a 126. Now I need to make a 36 out of it. I would need another 2 because there is one 6 and here is the other 6. Now I need to make a 96 out of it. To make a 96 out of it, I need to have 3, I have to have 12 8s are 96. I have to have 12 8s are 96. Do I have a 12 already? Yes, I have a 12 already using these three. Now another 8 is required. So 2 raised to the power 3 would be required over here. I'll quickly use it. Okay, 8 sevens are 56. 56 multiplied by 4 multiplied by 9 is my answer. 9 6 are 54. 9 5 are 45 is 50. Now this needs to be multiplied by 4. 4 4 are 16. 4 5 are 20. So 2016 upon 100 is my final answer. So 20.16 is my final answer of the LCM of the three terms that I have talked about above. Okay, I think we are good to go. Moving on. Find the LCM of the reciprocal of 22 and 16. The reciprocal of 22 is 1 upon 22 and the reciprocal of 16 is 1 upon 16. And I need to find the LCM. Whenever the LCM is required, that would be used in the numerator, and whenever the LCM is required, the HCF would go in the denominator. Okay, LCM upon HCF. The LCM of 1 and 1 is nothing but 1, and the HCF of 16 and 22. What is the highest number which can divide both 16 and 22 easily? The answer is 4. No, 4 is not going to be useful. 3, no. 2 for sure. So the answer is 2. The final answer that I come to is 1 upon 2. This is it. Okay, this is it. Now, there is a very serious concept which has been asked in multiple exams, and that concept says when I have two numbers, let's assume I have two numbers, a multiplied by b. The multiplication of two numbers would be equal to the HCF multiplied by the LCM of two numbers. Okay, it would be equal to the multiplication of the HCF and the LCM. Multiplication of two numbers is equal to the HCF multiplied by the LCM. Okay, kindly remember this. The LCM of two numbers is 840 and the HCF is 7. If one of the numbers is 56, find the other number. I'll use the same property I discussed in the previous slide. 840 into 7 is equal to 56 into x. Have 7 ones are, and then there is 7 8s are 56. Now 4 2s are 8, 4 2s are 8, 2 1 0. There's 1 and this is 105. So the number that I'm looking for here is equal to 105. The number that I'm looking for here is 105. Yep, I think we are good. So moving on. A and B are two prime numbers such that the value of A is greater than that of B and their LCM is 209. Find the value of A square minus B square. See, there are two numbers which need to be found out and I just have the value of one of them. Okay, there are two prime numbers. When both of them are prime, that means there are no common factors. There are no common factors. When in a situation there are no common factors, the deduction I have out of it is that the HCF is equal to 1. The deduction that I can make out of it is that the HCF is equal to 1 because there are no common factors. And why is that? Because in the question itself it has mentioned that there are two prime numbers. Prime numbers do not have more factors other than 1 in itself. How can we imagine them to have any extra factors other than itself? So here I can say that A multiplied by B is equal to the LCM multiplied by the HCF. The HCF being 1 and the LCM being 209, there are two numbers which when multiplied with each other give 209. And it has been mentioned that A is greater than B. Let me try to factorize 209. Let me try to factorize 209. How would I factorize 209? Let me try with the table of 7. 7 to the 14. 69, no, doesn't work. 8, no. 9, no. The sum of the digits is not divisible by 9 or by 3, no. 5, no. I think 11. 11 should do. Yep. I will have 11 ones are 11 and another 9, 99. 11 nines are 99. Okay. So this is 19. 11 multiplied by 19 gives me 209. So 11 multiplied by 19 gives me 209. A and B. 11 into 19. Okay, I think we are good. I think we are good. Yep, I think we are very good. 11 multiplied by 19. Now, as it has been said that A is greater than B, this means our assumption is wrong, that the value of A is 19 and that of B is 11. Okay, so this is a right assumption. The question has been asked, A square minus B needs to be found out. When A square minus B needs to be found out, I'll simply plug in the values of 19 square minus 11. The value of 19 square is nothing but 361, minus 11 would give me the value of 350. Would give me the value of 350, and this is going to be my final output. This is going to be my final output. Okay, moving ahead. The HCF and the LCM of two numbers are 8 and 48 respectively. If the ratio of two numbers is 2:3, then the larger of the two numbers is what? Okay, I already have the HCF of two numbers and I also have the ratio between the two numbers. If the ratio between the two numbers is this, then I can assume the absolute value of the numbers to be 2x is to 3x. We've already dealt with this in the chapter of ratios. So I'll use the same concept of HCF being multiplied by the LCM is equal to 2x into 3x. This gives me 6x square is equal to 8 into 48. 6 1 ja, 6 8 ja. So I have 64 is equal to x square. So I can easily say that the value of x is equal to 8. Now I need to find out the larger of the two numbers. The two numbers are split in the ratio 2:3. 8 has to be multiplied to both of them. So 8 2 is a 16 and 8 3 is a 24. 8 2 is a 16 and 8 3 is a 24. So when I'm here at 24, this is my final answer and this is my larger answer. Got it? Moving on. The sum of two numbers is 60 and their product is 875. The HCF of the numbers needs to be found out. Okay, so x plus y is equal to 875. Oh, I'm wrong. X plus y is equal to 60 and x into y is equal to 875. 875. I have two equations, I have two variables, and I need to find out the HCF of the two numbers. First of all, I would have to predict one of the two numbers. As the multiplication of the two numbers gives me a number which is divisible by 5, I'll quickly try to factorize this and try to find out two numbers which add up to 60. When I'll divide it by 5, I would get a number which is equal to 5 ones are 5, 5 sevens are 35, and 5 fives are 25. I'll get a 5 here. I'll take out another 5, which would make it 25, and this would become 35. So, yep, we found out two numbers which are 35 and 25, which when multiplied give the result as 875, and which when added give a result of 60. Which one added give a result of 60. Yep, 35 and 25 and a result of 60. The HCF of the two numbers. As I have declared that the two numbers are 35 and 25, I need to find out the highest common factor. Trying to find out which is the biggest prime number, which is divisible by both of them. 7? No. This is 7 into 5. This is 5 into 5. Okay, 5 into 5. So the highest number which is common to both of them is 5, and this is my final answer. Okay, this is my final answer. Moving ahead. Two numbers are in the ratio of 2:5. The LCM is 80. Find the numbers. If two numbers are, let's assume 2x and 5x, these are the absolute values. These are the absolute values. Just a second. Just a second. So 2x and 5x. Okay. So whenever we don't have the HCF of the numbers here. We don't have the HCF of the numbers here yet. So in such a case, what I would do is the LCM has to be multiplied to the two numbers in ratio. The LCM has to be multiplied by both the numbers in the ratio. But let me first find out the LCM of 2x and 5x. The LCM of 2x and 5x itself is equal to 10x, and the value of 10x is equal to 80. So this x, this 0 would get cancelled with 0, and the value of x would come out to be 8. As I have the value of x, I can now just put this value back and create the numbers now. Because I introduced x only and only because the numbers were in ratio form. I had to reach a point where I could find the absolute values of the numbers. So I'll put them back. 8 2 is 16 and 8 5 is 40. 16 and 40. 16 and 40. This is my output. Moving on. Find the greater number which exactly divides 15, 30 and 40. Find the greatest number which exactly divides 15, 30 and 40. This means I need to find out the HCF of 15, 30 and 40. Let me put them down to prime factorization. This comes out as 5 into 3. This comes at 5 into 3 into 2. And this comes at 5 into 2 into 2. Maybe another 2. Yes, this is it. Now the greatest number. Do I have 5 in all the 3 equations? The answer is yes. Do I have 3 in all of them? The answer is no. Do I have 2 in all of them? The answer is no. So the greatest number which exactly divides all 3 of them is 5. Okay, exactly divides 15, 30 and 40. Moving ahead. So there is this important concept number 14, which I would like to talk about. Concept number 14, which I would like to talk about. In concept number 14, we will study the applications of HCF as well as the applications of LCM. There are 3 major applications of HCF, and usually whenever you see the word largest, the largest number, you have to go for HCF, okay, the highest common factor. And whenever you see the smallest or the lowest number, at that time you have to go for LCM. I hope this is very clear to you. So what are we actually doing here? Whenever we have to find out the largest number which can divide x, y and z exactly, at that time we have to find out the HCF of x, y and z. This was the first case for HCF. Okay, this was the first case for HCF. Then secondly, find the largest number which can divide x, y and z and leaves a remainder of r in each case. Okay, leaves a remainder of r in each case. In such a situation, we will have to find out the value of x minus r, y minus r and z minus r. Okay, so the HCF of x minus y minus z and z minus x. This is our situation. This is our second situation for HCF. Talking about the third situation for HCF, find the largest number which can divide x, y and z and also leaves remainders which are a, b and c. At that point, what you are supposed to do is you have to take an HCF. Again, you have to take an HCF because the largest number has to be found out. So you'll have to take an HCF of x minus a, y minus b and z minus c. So these are the 3 areas that we have to focus on. These are the 3 options that we have to focus on 1, 2 and 3. Let's now talk about LCMs. Okay, let's now talk about LCMs. In LCMs, I need to find out the smallest number that is exactly divisible by x, y and z. Whenever the smallest number is needed, I would use the LCM. Okay, I would use the LCM. So that is the first point for LCM. Secondly, if I need to find out the smallest number which is divided by x, y and z and leaves a remainder r, at that time I have to find out the LCM of x, y and z and then simply add that remainder in the equation. I simply have to add the remainder in the equation. Then finally, this was the second point for LCM. Now coming finally to the third point of LCM. The third point of LCM says that find the smallest number k which is divided by x, y, and z and leaves remainders a, b, and c respectively. At that time, I would have to find out the LCM of x, y, and z, which I would assume to be k, and then k should have a value of x minus a, y minus b, and z minus c. Okay, x minus a, y minus b, and z minus c. So once see that the third example of LCM is definitely very typical. The third point is very, very typical. So whenever I'll encounter a question, I'll let you know that this is the same third application which sounded a little typical. Let me take you to the first question. The first question is here on the left hand side. Okay, I've already solved it in the last class. I know it very well, but I'll solve it one more time. I need to find out the greatest number that exactly divides 15, 30, and 40. Coming back to my equation, I need to find out the largest number which can be divided, which can divide these three numbers exactly. Similar question. So I would find out the HCF of 15, 30, and 40. 15, 30, and 40. So there is a good possibility that I'll quickly split it up. 5 multiplied by 3, 5 multiplied by 3 into 2, and 4 multiplied by 2, that is 8 multiplied by 5. So there is only one common factor, which is the highest common factor which I can see out of all the three equations that I have. Okay, so it is 5, 5, and one more 5. This output simply means that I have the HCF as 5. Okay, good enough. Let's move on. This is the second question. When 1062, 1134, and 1182 are divided by a number x, the remainder of each case is y. What is the value of x minus y? So let's assume that we have 1062, 1134, and 1182. Okay, and in this situation you are dividing all of them with the number x, and in each case there is a specific remainder y that is being left out. So I need to sort out how this thing works. So let's assume that these three numbers are being divided by a number which is the greatest number, and that number is equal to p, and it leaves the same number, it leaves the same remainder. So what I would do is I need to find out the HCF first. In the HCF pattern, what I would do is I won't be able to find out the HCF of these numbers alone. I would have to find out the gaps between them and then find out the HCF. The first gap is this. The second gap is 1134 minus 1182. And the third gap is 1062 minus 1182. From here, I would find out all the gaps that are required, and these gaps I would use to my benefit. Okay, I will use these gaps to my benefit. The first gap that I can see over here is that of 72. The second gap that I can see over here is that of 8 and 1 less. This is 48. And the next gap that I can see over here is that of 120. Yeah, is that of 120. So now I have easily digestible numbers available with me, and I need to find out the highest common factor over here. If you see pretty closely, I can see the table of 12 being played here. This is 12, 4s are 48, this is 12, 6s are 72, and this is 12, 10s are 120. Okay, so I have all these numbers with me. I need to find out the highest number which is available to my use. If I look a little closely, 12 is not going to be my answer because there is an element of 2 in all the other elements beside it. So I would use the element 2 and I would call that 24 is the HCF of my number, and this particular number that is 24 is the HCF is equal to x. Okay, so this is x which I have found out. Now I will have to manually divide 1062 by 24, and whatever remainder I get whatever remainder I get, I would use it to my benefit. Okay, that would be the value of y. So I'll quickly follow the long division method of 1062 divided by 24. 24 fours are 96. 96, this is 10 and 102. Then another 24 fours are 96 and I get a 6 over here. So 6 is the remainder that I was looking for, and that value is equal to that of y. I have the value of x with me, which is equal to 24, and I have got the value of y with me, which is equal to 6. So 24 minus 6 is nothing but 18, and 18 is the answer of my question. Moving on. What is the least number? See, we are now sitting at the least number, which when divided by 15, 8 and 36 leaves the same remainder 9 in each case, and is also divisible by 11. And is also divisible by 11. I'll quickly take you to the point. I'll quickly take you to the point where the LCM has to be found out. The LCM of 15, 8 and 36 needs to be found out quickly. So I'll split it out. 3 into 5 is the 15 and 8 cannot survive alone. So I will simply write 8 over here. 8 already has 4 in it and 4 nines are 36. I would write a 3 over here because I already have a 3 available with me. So this is my LCM of the equation. 8 5s are 40 and 40 nines are 360. Am I wrong somewhere? Just let me check. Just let me check. Whenever I was writing 3 over here, this was not right. Why? Because I already have 3 into 5 into 2 into 2 into 2 3 times. Now I need to make a 36 out of it. For making a 36, I need to have 4 and 9. I need to have 4 and 9. Or what else can I have? I can have 3 into 3. So this simple 3 can be useful over here. This simple 3 can be useful over here. The simple 2 can be useful over here. Yep. So here the value which comes out is, the LCM which comes out is 360, right? The LCM which comes out here is 360. Now I need to see a multiple of 360. Okay, 360x is a multiple of 360. A multiple of 360 which will always leave a remainder of 9, and it would also always be divisible by 11. Okay, so it is 360x plus 9 whole upon 11. 360x plus 9 whole upon 11. So I need to now use hit and try values. I need to now use hit and try values to solve this. So 360x plus 9 whole upon 11. What I'll do is I'll quickly divide it by 11 so that there is some material available to me which is easily divisible by 11. So 11 3s are 33. I have another 30. 11 2s are 22. So 332 we already have with me. So when I use 32, this means 352 x whole upon 11 would have done the job for me. Would have done the job for me because 352 divided by 11 is equal to 32. So 352x would have done the job for me. I would be left behind with an 8x plus 9. Now this 8x plus 9 must be divisible by 11. Why did I do this job? Why did I split it into some multiples of 11 and left some of them behind? There was a simple reason to it. There was a simple reason to it. And what does the simple reason say? The simple reason says that it eases down my calculation. This is easier to solve. This is easier to solve. So I'll now hit and try and put values of 8 with its multiples. I'll start with 0. I'll start with 1. I will start with 1. So 8 plus 9 is 17, which is not divisible. Okay, so I'll now go for 16 plus 9. 16 plus 9, again not divisible. I'll go for 3. I'll go for 3. 3 is 24. plus 9. This is equal to 33. This is equal to 33. This is definitely divisible by 11. This means that 360 can be multiplied by 3 and added a 9 to find out the least number, which follows all my rules. Now, when 360 is multiplied by 3, it means 3 6 are 18, 3 3 are 9, 1080 plus 9. This gives me the output as 1089. Okay, this gives me the output of 108 and 9. So this is my smallest number, which is divided by all of these numbers, and it gives the same remainder each time, and it is also divisible by 11. Okay, moving on. What is the least number that must be added to the greatest 6-digit number so that the sum will be exactly divisible by 294? So that the sum would be exactly divisible by 294. Okay, so let me first take you to the point where I have the greatest 6-digit number. The greatest 6-digit number is nothing but triple nine and another triple nine. Okay, triple nine and another triple nine. Now it needs to be exactly divisible by 294. It needs to be exactly divisible by 294. For my own luck or for my own game, what I would do is I would follow the long division route and try to take you to the answer. Okay, try to take you to the answer. Yep. So this is my number. I'll quickly start dividing it. I can't go 4 times, so I will definitely go 3 times. 3 4s are 12, 3 9s are 27, 28, 3 2s are 6. So this would give me 882. This would give me a number of 1179. Can I go 4 times? Can I go 4 times? Yep, I think so. I'll quickly try it once here. 4 4s are 16, 4 9s are 36, 37, 4 2s are 8, 1176. Yep, this is good for me. I have 1176. I'm left with 3. 1 9 was utilized here. 1 9 was utilized here. The second 9 I'm going to utilize now. 39 doesn't have a game with this, but I'll have to pull down another 399, another 9 over here. So I have 399 over here. Once I have 399, I'll go with 1, and I'm left with 294. I'm left with 294. This means the option here is 105. The option here is 105. So I'm left with a remainder. I'm left with a remainder out of this. This is the complete dividend. The divisor 294 when multiplied by 341. I would have to add a 105 to completely reach the largest 6-digit number. I would have to add a 105 to reach the highest 6-digit number. As I have reached the 6-digit number here, now this is an extra. This is an extra point over here. This is an extra over here. Let's assume that I remove 105 from this entire equation. I remove 105 from this entire equation. I remove 105 from here and I introduce a minus sign over here. Okay, I'll quickly remove 105 and I'll help you understand what's going on. Here's 4, here's 9, here's 8, and there is 999, 88. This is 999, 894. Now, what is this number? This number is the greatest 6-digit number. The greatest 6-digit number which is divisible by 294. This is the greatest 6-digit number which is divisible by 294. So I have that number over here. But what is the question that is being asked? What least number should be added to the greatest 6-digit number so that the sum will be exactly divisible by 294? This means that this is the second last multiple, or the last multiple which I'm looking for. I would have to add 294 to it to reach a point where I find the next multiple. Okay, or in similar, or in similar, or in like, or in easier terms, I should say that I have 294 with me. If I subtract a 105 out of it, I get to know that 189 is the number which has to be added. 189 is the number which has to be added. Or simply, or much more simply, I can say that double nine, double nine, and double nine, 6 times 9 has to be added, to 189 to reach a point where I get the next factor of 294. So my answer is going to be 189. Okay, my answer is going to be 189. Got it? My answer is going to be 189. Yep. Moving on. Now we'll be solving word based problems for HCF as well as LCM. Okay. Yep. It says it's nothing but example 13. Okay. 13 A, B, C are four numbers, and the HCF of each pair of numbers, 13 of A, 13 of B, 13 of C, is 13. Is 13, where A, B, and C are each less than 60, and A is the smallest one and C is the largest one. What is the value of A plus C whole upon B? See, when such a question is encountered by you, trust me, the solution is definitely going to be very easy. It says when I take each pair along with 13, this one, and this one, when I take each pair along with 13, I get the HCF as A. I get the HCF as A. When the HCF is coming as 13, that means that A also must be a multiple. A also must be a multiple, must be a multiple of 13. Similarly, B also must be a multiple of 13, and C also must be a multiple of 13. There is another condition that A, B, and C, this is the condition that A is the smallest, B is the middle one, and C is the largest. Also, each and every value is less than 60. This is also a condition. So what am I supposed to do with it? This means that all of them are multiples of A. This is 13 multiplied by something which is less than 60. Let's assume 2, which is equal to 26. This is 13 multiplied by 3, that is 39, again less than 60. And this is 13 multiplied by 4, 13 fours are 52, again which is less than 60. Okay, this is also less than 60. So I think I have my answer with me. The answer is nothing but 26 plus 52 whole upon 39. This means 2 plus 4 whole upon 3. 2 plus 4 whole upon 3, which is equal to 6. And this is my answer. All right. All right. The 5 bells ring together at the intervals of 3, 5, 8, 9, and 10. Okay. 5 bells ring together at these intervals. All the bells rung simultaneously at the same time. The question is, the bells will ring again simultaneously when? Okay. When such a question or when such a word problem comes, at that time, what you're supposed to do is, you're supposed to find out the LCM. Okay, you're supposed to find out the LCM. The LCM is 3 multiplied by 5 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by another 3, because I already have a 3 here, and which makes 9, and multiplied by 5 because I already have a 2 to make it 10. Okay, so what I get out of it? I get out of it this formula, which is 5 2s are 10, another 5 2s are 10. This means there are going to be two zeros, and then 3 2s are 6, 6 3s are 18. I have my answer as 1800, and this answer stands for 1800 seconds. This answer stands for 1800 seconds. Okay, I think we are good. The answer stands for 1800 seconds. Now, the question would be, when would the bells ring again? And 1800 seconds would be divided by 60. I need the answer to be in minutes. Okay, so this is done. This is done. I will have 6, and this is 30. So the question is, the all the bells would ring simultaneously after the next 30 minutes. Okay, all the bells would ring simultaneously after 30 minutes. Yep, good to go. So I'll move ahead. Find the greatest possible length, which can be used to measure exactly 4 meter 90 centimeter, 3 meters 85 centimeters, and 12 meters 95 centimeters. Okay, so these are the three lengths which are available to me. I need to find out the greatest possible number. As the word greatest is being used, I need to use HCF. Okay, I need to use HCF. What is the HCF? See, I'll tell you one thing. They are supposed to ring together simultaneously. They are supposed to ring together simultaneously. So I have to find out the shortest time. I have to find out the shortest time when they ring together simultaneously. But here, at the HCF, at the level of HCF, what am I doing? In HCF, I'm trying to find out what is the biggest size scale, or what is the biggest length that I can use at once to measure all three of them together. Okay, so 4 meter 90 centimeter, 1 meter is equal to 100 centimeters. So it is equal to 490. This is one, and then there is 385, which is the second one, and there is 1295. There is 1295. I'm supposed to take an HCF out of these. Whenever you find, whenever you find such a big number, whenever you find such a big number, and you feel that it is going to get really difficult to find out the HCF, what you can do is you can find out the HCF of the differences. You can find out the HCF of the differences. The difference between 490 and 385 is 105, and the difference between 1295 and 385 is nothing but 0, 1, and 9, 910. Okay, also the difference between 1295 and 490. Okay, I'll write 490 here quickly. This would give me a difference of 805. Difference is 805. So 805. So if I can find out the HCF of these three also, we will get a hint. We will get a lot of help. Okay, so let me quickly split it down. This is nothing but 75. No, 7. This is 7 ones are 7, and 7. This is 15 into 7. Okay, this is 15 into 7. What else can I see here? I can see that I have 9 10. So this is 13 multiplied by 7 multiplied by 5 multiplied by 2. Okay, 13 sevens are 91. 91 into 10 is 910. So what do I do about 805? I'll do it with 5. 5 16s are 80, and 161 into 5. I'll use another 7 to my rescue. This is 7 2s are 14, 7 3s are 21. So 23 into 7 into 5. Out of all the numbers that I found out here, out of all the numbers that I have found out here, out of all the numbers I have found out here, I can pretty evidently see that 7 and 5 are occurring multiple times. 7 and 5 are occurring multiple times. See, this is 15. So I'll split it into 7 into 3 into 5. So 7 and 5 are occurring multiple times. So I can easily say that the HCF of the three numbers is 35, and that is my final answer. Okay, moving on. See, Radha, Pratma, and Reena began to jog a circular path and they complete the revolutions in 50, 75, and 100 seconds, respectively. After how much time in minutes will they meet together at the starting point for the first time? Okay, it's talking about for the first time. When such a situation occurs, we are supposed to take LCM because it is asking us what is the shortest time in which they would meet together once. Okay, so for LCM, what I would do here is I'll firstly change the pen color, and then I would have 50, 75, and 100 with me. Now let's enter the big boys club or the big girls club and try to find out the LCM pretty quickly. Is 75 divisible by, like, is 100 divisible by 75? The answer is no. Is 50 divisible by 75? 50 divisible by 100? The answer is yes. So when such a situation comes that 50 and 100 is there, you have to pick out the bigger number to be the LCM. But 75 and 100 doesn't have the same equation as 50 and 100 does. So what I would do is I would multiply 100 with 3. This gives me a 300. So it satisfies all of them now. No, that is too much. Yeah, 300 is good. Yeah, 300 is good. So 300 is divisible by 100, by 75, as well as by 50. So I get the answer as 300 seconds. This 300 seconds has to be divided by 60 seconds to give the answer in minutes. So this goes here, 6 5s are 30. My answer is 5 minutes. Okay, my answer is 5 minutes. Moving on to the next question. Yep. So now I've come down to the most basic things that we learnt in school. Let's say that there is a number which is 42 and I am dividing it by 6. No, 6 is a bad number for this. 7, no, still a bad number. Let's assume I'm dividing it by 5. So what actually happens? I take 5 8 times and bring a number 40 over here. I'm given 2, and 2 is the remainder out of this equation. I will try to help you and denote what each and everything is called. The thing which is under the roof is basically called the dividend. Okay, this is called the dividend. This number which is used to divide the dividend is called the divisor. It's called the divisor. Now, whatever I have over here, this is nothing but the quotient. And whatever I am left behind in the end, which did not let my division to complete properly, is called the remainder. Is called the remainder. Okay, so I have all my things in place. If I need to find out what the dividend is, I can easily say that the divisor has to be multiplied by the quotient, and there needs to be an addition of the remainder. How do I practically do it? I need to find out what the dividend was. So the divisor here is 5. I would multiply it with the quotient, that is 8, and I would add a 2 at the end. So what I'm left with is 5 8s are 40. 40 plus 2 is 42. And this is my final output. Which is 42. Yep. So I think we are good. So I'll quickly solve the question now. On dividing a number, let's say the number is n, by 38, on dividing a number n by 38, the quotient comes out to be 24 and the remainder comes out to be 13. What is the number? I'll quickly give you a small graphical representation. Graphical doesn't actually mean in the graph, doesn't actually mean in a graph. The number was divided by 38. This means 38 is the divisor. The quotient that was received was 24. So this is quotient. And whatever was left behind was nothing but a remainder of plus 13. So how do I get the dividend back? How do I get the number back? I will simply multiply 38 with 24 and add a 13 in this equation. And add a 13 in this equation. So I'll quickly do this. 2 8 is 16. This is 760. Okay, this is 760 when I multiply it by 20. What about multiplying it by 4? 4 8 is 32. I have a 3 in back. 4 3 is 12. 12 plus 3. 12 plus 3 is 15. Yeah, 12 plus 3 is 15. So I get a 2 over here. I get an 11 over here. And this gives me a 9. So I already have a 912 with me. And I add a 13 to this, which gives my answer to be finally 925. This gives my answer to be finally 925. I hope we are good with this. I hope we are good with this. So I'll move on. Okay. The divisor of 10 times the quotient and 5 times the remainder in a division fun and in a division sum. What is the dividend if the remainder is 46? The divisor of 10 times the quotient and 5 times of the remainder in a dividend sum if the remainder is and the remainder and 5 times the remainder. Okay, so there is, in this particular question, it seems to be a little tricky. It seems to be a little tricky, but I'll still try to find out what this is actually saying. So this question was turning out to be a problem for us, but the reality is much different. The question has a small error. The divisor is 10 times the quotient and 5 times the remainder in a division sum. What is the dividend if the remainder is 46? Okay, I'll quickly write down whatever is written in front of me. The divisor is equal to 10 times the quotient. It's also equal to 5 times the remainder. And the value of the remainder has already been given to me as 46. Okay, so the remainder is 46 over here. If I use this remainder over here, I have d as 5 times 46, which is also equal to 230. Okay, so 230, I have already found it. I've already found my divisor. I need to find the dividend finally. I'll now take to the question, to the quotient. The remainder is already 46. I need to find out the quotient. If 10 times the quotient is equal to 5 times the remainder, I'll cancel out 5 ones are, 5 twos are, and I can say the quotient is equal to the remainder upon 2, which is also equal to 46 upon 2 or 23. So I can easily say that the value of the quotient is 23. And if I have all these things, if I have all these things available to me, I can say that 230 multiplied by 23 plus 46 would give me my dividend, because the formula of the dividend is equal to divisor into quotient plus remainder. Dividend is equal to divisor into quotient plus remainder. Okay, I hope we are good with it. So this is square of 23. The square of 23 is nothing but 529. I'll do it here at the corner. The square of 23. Okay. 3 3 is 09 and 2 2 0 4. 3 2 is 12. 12 2 is no 3 2 is 6. 6 2 is 12. I have 120 here. So this comes out to be 529. So I have 5290 available with us. Plus 46 is also there. So once this equation is in place, I can easily say that my answer is nothing but 5336. My answer is nothing but 5336. And this is my final call. Okay, this is my final call for this answer. Moving on. Moving on. See, there is a concept that that the remainders, the remainders are operationable, that the remainders are operationable. We've already learned that. It means that if I have seven numbers with me, I have 7, 3, and 9, and 11 with me, and I'm dividing all of them with 2. Okay, let's assume that I'm adding also all of them up and also dividing them by 2. So when such a situation comes, I'll get the remainder as 1, I'll get the remainder as 1, I'll get the remainder as 1, and here also I'll get the remainder as 1. So once there is again a plus sign between them and I also have a 2, so I will have 1 plus 1 plus 1 plus 1, which makes it 4 whole upon 2. This would give me the remainder as 0. So when they were all unilateral, when they were all alone, they were producing 1 as remainders. But when they got scot free, or when they all came together, they produce remainders as 4 by 2, which is equal to 0. So what I'm going to do here, I'm going to add all of them up one more time. 11 plus 9 is 20, 20 plus 10 is 30. So 30 upon 2, this means the remainder is equal to 0. So when such a situation comes up, when you have multiple remainders available, remember that the remainders are operationable. Okay, the remainders are operationable. I hope I'm good with that. Moving ahead, find the remainder of 2, 7, 9, 11 whole upon 5. I'll try to find it out separately, and I'll also put an operation. I'll first perform the operation and then come to my conclusion. Okay, so when I say 5 upon 2, I get plus 2. For 7 by 5, I get a plus 2, and for 9, I get a plus 4, and for 11, I get a plus 1. I add all of them up. 2 plus 2 plus 4, 4 is this is 9. Yep, I think this is 9, and 9 by 5 would ultimately give me plus 4 as the remainder. This is pretty useful. This is very, very useful when big numbers are given to you. Okay, this is very, very useful when big numbers are given to you. Okay, moving on. Okay, if each of the two numbers 5 raised to the power 16 and 5 raised to the power 25 are divided by 6, the remainders are respectively R1 and R2, then what is the value of R1 plus R2 whole upon R2? Okay, so we've encountered a very beautiful question with us today. Just simply see how well I'm going to use it. I have 5 raised to the power 16 with me. I have 5 raised to the power 25 with me. And I go for a division by 6. I go for a division by 6. So 5 upon 6, 5 upon 6. So the difference between 5 and 6 is that of minus 1. I can take this concept to a negative remainder of minus 1. Okay, I can take it to a negative remainder of minus 1. So when I say there's a negative remainder of minus 1, it would be raised to the power of 16. Similarly, if I take it to the negative power of minus 1, it would be raised to the power of 25. Now I'll help you understand the concept of even powers, and I'll help you understand the concept of odd powers. Whenever a negative number is given an even power, the output comes out to be a positive number. Okay, so minus 1, when coupled up, it would get cancelled out and finally give me the remainder of 1 by 6. The remainder of 1 by 6. Okay, so I think we are good with this. Now I have a minus 1, and this is going to be an odd deal. This is going to be an odd deal. So the minus 1 is going to remain and 6 is going to stay here. When I assumed that there is a 5 by 6, the minus 1 remainder came. So if I still have the minus 1 remainder with me, I would now focus on this, that this may be called 5 by 6. So the remainder which I get from here, R1 is 1, and the remainder which I get from here, R2 is 5. The question being asked to me is R1 plus R2 whole upon R2. R1 plus R2 whole upon R2. So what I get out of it is 1 plus 5 whole upon 5, which is nothing but 6 by 5, which is nothing but 6 by 5. Okay, which is nothing but 6 by 5. I think we are good to go. Okay, so moving to the next concept. As I've already said that remainders are operationable, so the questions which are going to come up further are also going to have the same property. Okay, now 522 is being multiplied by 361 and both of them would be divided by 5. The remainder needs to be found out. See, in such a situation, when remainder needs to be found out and two big numbers are being multiplied with each other, what I would do is I would use the remainders separately first. I would go for 522 divided by 5. It is easily visible that 2 is going to be the remainder 1. Now, talking about 361 divided by 5, it can be easily seen that the unit digit is going to be the remainder. So, I can say that R2 is the remainder. R2 is the remainder. So, and this is 1. Okay, this is 1. So, if the first number was being multiplied by the second number, the remainders would also be getting multiplied now. That means I have a 2 over here and I also have a 1 over here. 2 multiplied by 1 divided by 5. This gives me a remainder of 2 when it is upon 5. So, remainder 2 is the answer for this question. Moving ahead. If 7 divides the integer n, then the remainder would be 2. What would be the remainder if 9n is divided by 7? Okay, so all I'm saying is when n is divided by 7, when 7 divides the integer n, then the remainder is 2. What will be the remainder if 9n is being divided by 7? I can split this apart. I can say 7n whole upon 7. I can say 7n whole upon 7. Right? I can say 7n whole upon 7. See, here we had 1n. If I have 9n, what I'll do is I'll multiply this entire equation by 9n. So this would give me 9n upon 7 plus 18. I'll multiply this whole thing. So what will be the remainder if 7n is divided by 7? So 7n has been divided by 7. This is visible to me. Now I have another 18 over here. When I divide 18 by 7, I get it at 7 2s are 14 plus 4 is the remainder for me. Okay, plus 4 is the remainder for me. So D is my answer. Got it? Moving on. See, now there are two equations that need to be taken in consideration: ax square plus bx plus c. Okay, this is one standard form of an equation which is equal to y. Now this equation will have to be divided by another smaller degree equation. When this situation comes up and another smaller degree equation has to be divided, that time what do I do? Let's say the other equation is mx plus c. What do I do when this division has to take place? What I do is I put that the value of mx plus c is equal to 0. I try to find out the value of x, which is equal to minus c by m, and then I use this value of x as minus c by m and plug it. Okay, where do I plug it? I plug it in the top equation. And that is how whatever I'm left with in the end, if it is 0, it means it was completely divisible. If it is not 0, if it is any number, let's say the number was n, so that number which will be left behind would be my remainder. Okay, the number which would be left behind would be my remainder. I hope I've made myself clear. I'll quickly follow it for you. Yep. Find the remainder when we divide this big equation by this small equation. Okay, I'll just write it down for you. Okay, this is 3x raised to the power 4 minus 2x square plus 4x minus 1. So this is the equation with me. I will divide it by 2x minus 1. Okay, I will divide it by 2x minus 1. I will divide it by 2x minus 1. The equation is in place. What I'll do, I'll use this denominator and try to put it as equal to 0. So I already have it as 0. So I have the value of x upon 1 by 2. X is equal to 1 by 2. I'll use this value of x is equal to 1 by 2 and plug it in the numerator of my choice. I have 3x raised to the power 4. This means 1 by 2 raised to the power 4 minus 2 multiplied by 1 by 2 whole square plus 4 multiplied by 1 by 2 minus 1. 3 by 8 minus 2 by 4 plus 4 by 2 minus 1. So whatever the output would come would be my final remainder. Okay, this 2 by 4 is 1 by 2. This 4 would become 2 when it is cancelled out. So I get 3 by 8 minus half plus 2 minus 1. So this minus 1 and this, I'll just quickly figure it out. Okay, 2 plus 3 by 8, it is 16 plus 9, 16 plus 3, 19 by 8 minus 3 by 2. I'll quickly multiply a 4 here, I'll multiply a 4 here. I get as 19 minus 12 whole upon 8. Then I reach a point where I have 7 upon 8. I have 7 upon 8. Okay, 7 upon 8. So this is my remainder. Okay, I hope you've gotten a hang of whatever I'm trying to say here. Moving to the next concept. See, n is 2 raised to the power 48 minus 1 and n are exactly divisible by two numbers between 60 and 70. What is the sum of those two numbers? Okay, this is a very interesting question. Just hang in for a moment. So now we'll be talking about successive remainders. What happens in the concept of successive remainders is that I cannot really talk about it without using an example. And this is the only question we have that has been asked, and the example I'll be using it as the example. Okay. So the question says when a number is successively divided by 3, 4, and 7, the remainders obtained are 2, 3, and 5, respectively. What will be the remainder when 84 is divided by the same number? Okay, so I'll first of all try to find out the number. I'll keep all of them together. 3, 4, and 7. These are the divisors, and these are the remainders. 2, 3, and 5. Okay, these are the divisors, and these are the remainders. So what do I do with them? I don't have the quotient with me. So we will assume that the quotient is nothing but equal to 1. So 7 into 1 plus 5 would give me my first number, that is 12. Now I would use this 12 and apply it as a quotient in my upper one. Okay. So I multiply it by 12 and add a plus 3. So 4 12s are 48. 48 plus 3 is 51. Okay. So 51. Then multiply it by 51 here. 3 multiplied by 50 is 150. 150 plus 3 is 153. 153 plus 2 is 155. So I have received that number, and that number is nothing but 155. So as we have the number with me, now what would be the remainder when 84 is divided by the same numbers? Okay, we have 84 with us now. Yep, we have 84. Now I need to find out the remainder. So if I have 84 over here and I have a remainder of 150, I have this 155 as a dividend. I'll try to find out the remainder. 84 to 82 is 160. So I will simply subtract both of them. After the subtraction, what I get is 71, and my number is, the number that I was looking for is nothing but 71. Okay, I hope you've understood the concept of successive remainders. Moving on, two numbers different by 3951. Let's assume the first one is x and the second one is y, and I'm also assuming here that x is greater than y. If x minus y is 3951, when the larger number is divided by the smaller number, then the quotient is 12 and the remainder is 13. So if I have to put it here like this, when the larger number is divided by the smaller number, this is the larger number with me and here is the smallest number, the quotient that I receive is 12 and the remainder that I receive is equal to 13. If I have to recreate the larger number, I can say that the value of x is equal to 12 multiplied by y plus 13. The first equation out of my part was this, and the second equation out of my part is this. Now I'll quietly rewrite these equations. 12y, or simply x minus 12y is equal to 3. This is the second equation, and x minus y is equal to 3951. I'll subtract the two equations. Okay, so this 3951 turns itself into 3948, and that too of a minus. The x gets cancelled and I get an 11y over here. Okay, and the 11y is also that of a negative sign, minus 11y. Okay, so the minus and the minus get cancelled. I have 111 here. Then I quickly solve it. 11 3s are 33. I'm left with 64. uh, 64, 11 5s are 55 and a 98. No, there's an 88 here. There is an 88 here. So that 88 gets here. So the value of y that I receive is 358. The value of y that I receive is 358. Yep. So I just simply have to put it back into the first equation. Then 3951 plus 358 would give me the value of x, which is nothing but 9. This is 34309. It's asking me the sum of the digits of the larger number. Okay, it's asking me the sum of the digits of the larger number. So the sum of the digits of 4 plus 3 plus 0 plus 9 needs to be found out. 9 plus 3 is 12. 12 plus 4 is 16. So my final answer comes out to be 16. Got it? My final answer comes out to be 16. I hope you've understood. Moving on. When 200 is divided by a positive integer x, the remainder is 8. How many values of x are there? Let's assume that 200 was divided by some number, let's say n, and a remainder was left behind, that was 8. It means hmm, it means if 8 is removed out of 200, that number which is achieved, which is 192, whatever n is, it is a multiple or it is a factor of 192. Now there is an important thing to note. There is a very important thing to note. And what is that thing? That thing is that whenever I have 192, and it is saying that the remainder is 8, then the factors of 192, then the factors of 192 cannot be less than or equal to 8. In the beginning of the chapter itself, I have taught you a method to find out the number of factors of any number. Okay, remember? I'll quickly prime factorize it down. I have a 2 over here. Now let me straight away take it to 4. An 8 will do? Yes, an 8 will also do. What about a 16? Yep, a 16 would also do. So I have 2 raised to the power 4 with me. 16 goes away. 16 ones is 16 and 16 twos are 32. 16 ones is 16 and 16 twos are 32. This means 2 raised to the power 4 multiplied by 12. This means 2 raised to the power 6 because the 4 comes from here. 2 raised to the power 6 multiplied by 3. So the total number of factors are 6 plus 1 multiplied by 1 plus 1. 6 plus 1 multiplied by 1 plus 1. This gives me 7 into 2, which is equal to 14. This 14 stands for the total number of factors of 192. Okay, this 14 stands for the total number of factors of 192. And this also includes 1 and 192 itself. I just need to have all the factors which are above 8. Okay, which are above 8. So what I'll do, I'll try to figure out what are the factors of 192 which are less than or equal to 8. First of all, 8 is definitely a factor. So I'll start with 1 first. 1 is a factor, 2 is a factor. Let me quickly add the digits. Yes, 3. 3 is also a factor. I've checked here. What about 4? 4 is a factor. 5 is not a factor. What about 6? 6 3s are 18, 6 2 are 12. Yes, 6 is a factor. What about 7? 7 2s are 14. No, it doesn't work. What about 8? 8 is also a factor. So out of the 14, there are 6 factors which are of no use to me. There are 6 factors which are of no use to me. So my final answer is 14 minus 6, which is equal to 8, and 8 is my final answer. I hope you understood why I took the factors out of equation which were less than or equal to 8. Because the remainder I am getting is already 8. If the factor is smaller, then the remainder would also become smaller than it. So I hope you've gotten to understand where I'm coming from. On dividing a certain number by 363, we get 17 as a remainder. Okay, 363 is divided by a number, let's say x, we get a remainder as 17. What about the same number is divided by 11? What would the remainder be? What would the remainder be? I'll quickly divide 363 by 11 first. So 11 ones are 11, 11 threes are 33, 11 threes are 33. It means that this 363 will not have any effect on my answer. But what about dividing it by 11? When I divide 17 by 11, I receive the remainder equal to 6. And that is all. That was what was asked by me. What is the remainder? So this is the final remainder. So we have this question with us, which is example 5. I need to find out the least number which when divided with all of these leaves 4 as a remainder. And when the remainder is left, there is another clause. The clause says that it should be divisible by 7. So when it says the least number, I'm sure that I need to take the LCM from the equation. And when I need to find out the LCM, I'll find out the LCM of 12, 18, 24, and 30. Okay. My quick way of taking the LCM is 2 into 2 into 3. I've dissected down 12. Then I need to make an 18. So 9 2s are 18. So this is 9 and I already have 18 with me. Now 6 4s are 24. I need another 2 or 8 3s are 24. I have 8 with me. 24 is also found over here. Now a single 5 will do the game for me. This makes up 10, which is 0. And then 3 3s are 9, 9 4s are 36. So 360 is the LCM that I'm looking for. Okay. 360 is the LCM that I'm looking for. Now, in this number, 360 is the least number, which when divided by, we've solved the question till here. Now I need to move forward. It leaves 4 as a remainder. That means I'll have to add 4 over here and I would get the number as 364. Okay, I'll get the number as 364. Now, as I have the number 364, it says it leaves 4 as a remainder in each case. This has been done. But when divided by 7, it leaves no remainder at all. Okay, when divided by 7, it leaves no remainder at all. In such a situation, what I'll do is I'll divide 364 by 7 and no, there's one small silly spot which I missed. I have 360. 360 times something plus 4 should be divisible by 7. This is my concept. Okay, so I'll quickly divide 360 by 7, and I get 7 5s are 35 and another 10, so 7 1s are 7. I get 51n plus 3n as my remainder on 7 plus 4. So what I need to do is I need to find out the value of n where 3n plus 4 is divisible by 7. For n, I have to start from 1. Let me put the value 1 over here. When 1 is put as n, I get the output as 3 plus 4 whole upon 7. So I can easily find out that 7 is divisible by 7 over here, and I have my output of n equal to 1. I'll put this value n back to the first equation. What does the first equation talk about? It says 360 multiplied by 1 plus 4, which gives me my answer as 364. So 360 is the number which, when divided by 12, 18, 24, and 360, leaves 4 as a remainder each time. But when divided by 7, it leaves no remainder. Okay, so I have solved the question. I hope nobody faced any problem in this. All right, moving on. Which is the greatest number of 7 digits which, when divided by 10, 15, 20, 24, and 30, leaves remainder 6, 11, 16, 20, and 26 respectively. Okay, when you have multiple numbers to be divided from which are leaving multiple remainders, the question will stand true, or the question would be solvable only and only when the gap between the divisors the gap between the divisors and the remainders are equal. Okay, when the gaps are equal, the question is definitely right. So I'll check with 10 minus 6, the gap is 4. I'll check with 15 minus 11, the gap is still 4. 20 minus 16, the gap is still 4. Similarly, I can see with 24 and 20, the gap is 4. 30 and 26, the gap is 4. So I'll quickly take the LCM. I'll quickly take the LCM of 10, 15, 20, 24, and 30. Okay, the gap which is 4 over here, this is basically the remainder which would come in the end, and the remainder in this case would be subtracted. The remainder in this case would be subtracted. So first of all, let me quickly do the LCM. The LCM starts with 2 multiplied by 5 multiplied by 2, that would make it 20, and multiplied by 3 would make it 15. And I need 3 8s are 24, so another 2 would do my work. 3 8s are 24. Then I already have 30 with me because 5 2s are 10 and 10 3s are 30. Okay, so I have 10 over here, then 3 into 4 12. I have 120 as my LCM. Okay, I have 120 as my LCM. Now I need to compare it with the greatest number of 7 digits. I need to compare it with the greatest number of 7 digits. What is the greatest number of 7 digits? The greatest number of 7 digits is 7 times 9, triple nine, another triple nine, and one more 9. So I have triple nine, triple nine, and 9. So I have the greatest number of 7 digits over here. Now, if I add anything to it, this number would change itself into an 8-digit number. This number would change itself into an 8-digit number, but that is not my requirement. That is not my requirement. What is my requirement? The requirement is that I need to keep it a 7-digit number. This means I will have to subtract things out of it. I will have to subtract things out of it. So what do? I take the greatest 7-digit number and see till what time is it divisible by 120. Till what time it is divisible by 120. I say 128 the answer is 960. I get a remainder of 39. I pull down another 9 from there, and 123 is I get another 360 here, then again 39. I pull down another 9, then another 3. I pull down another 360 and another 39. This process would go on till I reach a point where the remainder in the end will remain 39. So what does it actually mean? It means that from 7 times 9, if I remove 39, from 7 times 9, if I remove 39, I reach a number which is divisible by 120. That means the number is 5 times 9 and a 60 at the end. 5 times 9 and a 60 at the end. So this number is divisible with the LCM of all these numbers. The LCM of all these numbers is equal to 120. Okay, so I am done with this point. Now I need to have a remainder as well. And when there are multiple remainders given, I've already told you that the remainder which is useful to us, the remainder which is useful to us is the remainder after the divisors and the remainders are subtracted from each other. Okay, so in the end there is a subtraction that is required. So double nine 960 minus 4. This 4 is the useful remainder for us, and double nine 956. This is my number which I was looking for. This is the greatest 7-digit number. It is also divisible by all these numbers with me. Perhaps, but consequently, it is also leaving a remainder of 4. A remainder of 4 common for all the numbers. Okay, every time let's just quickly see it. No, if I divide it by 10, I am left with a remainder that is 6. So this is pretty much evident that my question is solved over here. Good enough. Let's move on. Okay. 2 raised to the power 24 minus 1 is divided by 7. What is the remainder? 2 raised to the power 24 minus 1 whole divided by 7 is my question. In such a question, what I do is I try to find out a number in the numerator which is close enough to 7. I'll quickly do the exponents of 2. 2 square is equal to 4. 2 cube is equal to 8. So if I use this identity and write a cube over here, I'm already using 3 out of 24. So 8 are left behind. 8 are left behind. As I've told you previously as well, if 8a is given and I say that xb whole upon whole another bracket of c, another exponent of c, then I can easily say that the value of a is equal to b multiplied by c. So I've used the same identity over here. 2 raised to the power 3 and another 8 minus 1 whole upon 7. Whole upon 7. This gives me 8 raised to the power 8 minus 1 whole upon 7. Now I can split them apart in two areas. Splitting them means 8 upon 7 minus 1 upon 7. So this 8 upon 7, when I quickly try to figure out what is the remainder, if 8 is divided by 7, the remainder is 8. So, sorry, the remainder is 1. This 1 can be given the same power of 8 according to the question and according to everything that we've learned in the past. Then I will have 1 by 7 here again. So 1 raised to the power is 8 is nothing. It is 1 by 7. And I would do another 1 by 7. And I sorted. And I'm given the value of 0. So the remainder is nothing but 0. I hope I've made myself very, very clear. The remainder is nothing but 0. Moving on. What will be the remainder when 27 raised to the power 27 plus 27 is divided by 28? Okay, I'll quickly do it. 27 raised to the power 27 plus 27 is whole divided by 28. I'll split it into my own terms, the ones which I like. It means 27 upon 28 raised to the power 27 plus 27 upon 28. Okay, as I've already said, whenever you will have a number which is pretty close to the denominator, it's going to be 27 upon 28. I can also write that this is minus 1 to the power 28. Minus 1 to the power minus 1 divided by 28. So if the value of 27 upon 28 in terms of remainders is minus 1 upon 28, I can easily write minus 1 to the power 27 whole upon 28 plus 27 whole upon 28 plus 27 whole upon 28. When I use the power of minus 1, when I use the power of minus 1 and when I use the term minus 1 and give it a power which is odd in nature, so the negative thing will not remove itself, it will stay. This means the remainder is minus 1 upon 28 and plus 27 upon 28 plus 27 upon 28. In such a situation, what you're supposed to do, you're simply supposed to solve the numerator. The numerator says 27 minus 1, which is nothing but 26 upon 28, and 26 is clearly my remainder. 26 is clearly my remainder. So whenever you encounter such a question, try to dissect it down to the most simple form, to the most basic form, and once you've achieved that, you will be through. Okay, moving on. 19 raised to the power 19 plus 20 is divided by 18. What is the remainder? I'll quickly do it. 19 raised to the power 19 plus 20 whole divided by 18 is my question. In such a situation, I'll dissect the problem. 19 raised to the power 19 by 18 plus 20 upon 18. From this area, I can see that the remainder is equal to plus 2. From this situation, I can say the remainder is plus 1 raised to the power 19 whole upon 18, or simply 1 upon 18. Okay, simply 1 upon 18, or I can again say that the remainder is nothing but plus 1. So I have two remainders, plus 2 and plus 1, which I have obtained by dissecting the entire situation, and what I get out of it is the total remainder being plus 3. Okay, the total remainder being plus 3. Okay, so we've gotten our answer as plus 3. Moving to the next question. What is the remainder when 3 raised to the power 8 is divided by, it's not divisible, it's divided, it's divided by 7. Whenever 3 raised to the power 8 is divided by 7, I need to dissect, or I need to bring the power of 3, which is pretty close to 7. So I'll quickly do the exponents of 3. 3 raised to the power 1 is 3. 3 raised to the power 2 is nothing but 9. So I'll use the 3 raised to the power 2 and put a power of 4 on it. When 2 is multiplied by 4, I get an 8, and this is equal to the same power 8 as I have talked about. Okay, so I will use it in this manner. I'll use it in this manner. I'll call it 9. 9 raised to the power 4 whole upon 7. When I see 9 and 7, when I see 9 and 7, I tend to reach a point where plus 2 is the remainder. When plus 2 is the remainder and it's raised to the power 4, I reach a point which is 7. Okay, I give a power of plus 2. I give a power of plus 2 and I put it to the level of 4. I put it to the level of 4. So 2 raised to the power 4 is nothing but 16. 16 whole upon 7. This is plus 2. This would again give me a remainder of plus 2, because 7 2s are 14, and I'll again be left with 2. So 2 is my answer over here. Okay, 2 is my answer over here. I hope I made myself very, very clear. Moving on. Okay, what is the smallest square number that is divisible by both 10 and 15? Okay, whenever you find such a situation where you have to find the smallest number, as I've already told you, LCM has to be taken. LCM has to be taken. So I'll quickly take an LCM of 10 and 15. I can easily say that the LCM is 30. Okay, but every time that happens, 3, 2 multiplied by 5 is 10, and another 3. Now you need to find out the smallest square option. You need to find out the smallest square option. In any situation, when a smallest square is required, at that time, whatever prime factors you have, whatever prime factors you have, they have to occur, they have to occur in pairs. Okay, they have to occur in pairs. Always, okay, they have to occur in pairs. 2, 5, and 3. They have to occur in pairs. How do they occur in pairs? I'll have to have a 2 for a 2, I'll have to have a 5 for a 5, and I'll have to have a 3 for a 3. So in this situation, I get 5 2s are 10, 5 2s are 10. This is 00, and 3 3s are 9. So I have 900. So 900 is the smallest square number that is divisible by both 10 and 15. Okay, is the smallest square number which is divisible by both 10 and 15. Okay, I hope I made myself very clear of how I proceeded in this entire situation. Okay, moving on. Okay, let x be the least number. Let x be the least number divisible by all these numbers, and x is also a perfect square. This question is not much different. This question is not much different as and when compared to this question. Okay, you just have to be really sharp and really sure about the prime factors of how they occur. Okay, you have to be really clear about the prime factors and how they occur. So I'll quickly do the prime factorization, and in the end I need to find out the remainder when that number x is divided by 123. When that x is divided by 123. So what's the deal over here? The deal says I have 16 over here. So 2 into 2 into 2 into 2. So this is 16. I have 16 available with me. I have 16 available with me. Now I need to find out 20. I need to find out 24. No, now to find out this 24, I have to have an 8 multiplied by 3. So a simple 3 would do my deal. Okay, a simple 3 would do my deal. Moving ahead. Moving ahead. I have a 3 over here, and I'm done with 16 and 24. Further, I need a 30. As quickly as when I introduce a 5 in the situation, as soon as when I introduce a 5 in the situation, I get to 30. Okay, why? Because 3 to the 6 and 6 5 is a 30. I have a 30 available with me. I have a 30 available with me. Now, I need to find a 36. A 36 can come only and only with the help of 9 into 4. 9 into 4. So I already have a 4 available here. I need to create a 9. So I'll multiply a 3 with it. Okay. I'll multiply a 3 with it. I'll multiply a 3 with it. So I've gotten 36 as well. Now I need to check if I already have 45 or not. It means 9 5s are 45. It means 9 5s are 45. I have a 9. 3 into 3, 9. 9 5s are 45. I have a 45 available with me. Okay. I have a 45 available with me. So what do I actually do with it? What do I actually do with it? I have a 5. I have a 2, which is 10. Then 3 into 3 is 9. Now this entire LCM has been achieved. This entire LCM has been achieved. No, I think I am taking you a little in the wrong direction. A little in the wrong direction. Okay. I have this number. This number is the LCM that I was supposed to achieve. Now, to make a perfect square out of it, to make a perfect square out of it, I need to have all the prime factors available in pairs. Do I have a pair of 2? The answer is yes. Do I have a pair of these two? The answer is yes. Do I have a pair of 3? The answer is yes. What do I not have? The only thing that I don't have is a pair of 5. So I will introduce a multiplication of 5 in this entire equation. I'll introduce a multiplication of 5 in this entire equation. So let me quickly find out what is the value of x. The value of x comes out to be, this is 4, 4 is a 16, 16 5s are 80, and 85s are 400. 409s are 3600. So I have the value of x as 3600. I have the value of x as 3600. Okay, so I'm in my place and I'm in a situation where I'm doing okay. Okay, I'm doing okay. I have 3600. So this is the perfect square. Now I need to find out what is the remainder when 3600 is divided by 123. When 3600 is divided by 123. No problem. Yeah, 3600 is being divided by 123. 3600, I think 123 threes are no, that will be too much. So twos are 2 threes are 6, 2 twos are 4, 2 ones are 2. I have a 4 over here, I have a 1 over here, I have a 1 over here. I get 114. So 1140 is where I reach. 1140 is where I reach. So I have a 123. If I go for a 9, I go for a 9, I can do it. 9 threes are 27. 9 twos are 18, 20. 9 ones are 9, 9 ones are 9, and this is 11. 11 not 7. So this answer comes out to be 33. So the remainder finally is 3. I hope you are able to understand the steps that I took. I hope you are able to understand the steps that I took. Okay. The perfect square level was achieved over here. I introduced a plus, I introduced a multiplication by 5. I introduced a multiplication by 5. The multiplication by 5 helped me make this thing a perfect square. And ultimately, I just used simple long division. I used simple long division to reach the conclusion that the remainder in the end is going to be nothing but 33. Okay, the remainder is going to be nothing but 33. Okay, moving on. What is the smallest perfect square number which is completely divisible by 469, 4, 6, 9, 12, and 5? Okay, smallest perfect square. The smallest number is required, so I'll take the LCM. 2 multiplied by 2, this is 4, and then another 3 would create a 6, then another 3 would create a 9, then another 3 fours will become a 12, and another 5 would make it a 15. So I have the LCM clearly available with me. In this, I need to find out pairs, or I need to find out couples. This 2 has a couple of its own. This 3 has a couple of its own. This 3 has a couple of its own. But if I look at 5, 5 doesn't have a couple. So this 5 needs to be multiplied with 5. So I'll quickly multiply all of them together. 4 25s are 100, and there is 9. So my answer is 900. Okay, my answer is 900. I would want you to pause and seriously just try to figure out what I have done. I have introduced a new 5 just to couple it up. Okay, just to couple it up. Just to couple it up. Okay, so I'll move forward. I'll just quickly go through all the questions that I'm left with. See, this question which I'm talking about over here is a little difficult question. So I'll first solve this one on the right, and then I would come back. Here on in concept number 3, I'll be talking about AP and GP. I'll be talking about AP and GP. Here, there is just one question of perfect square which is left. Then I'll go to this question, and then I'll come back to AP GP area. Okay, let me do this. What is the least perfect square which is exactly divisible by each 14, 84, and 28? 14, 84, and 28. If you clearly see, everything written over here is a table of 14. Okay, so I'll multiply 2 with 7, which makes it 14. Another 2, another 2 makes it 28, and another 3 is required, which makes it 84. Okay, so I have 84 over here, and this is nothing but the LCM of all these numbers. I have the LCM of all these numbers. Now I need to make a perfect square out of it. To make a perfect square out of it, I need to have pairs. 2 and 2 become a pair. 7 and 3 are alone, so I'll have to introduce couples of them. Okay, I'll have to introduce couples of them. So what do? I have a square of 49, I have a square of 2 which is 4, and then I have a square of 3 which is 9. When I solve this equation, that is when I get my answer. 9 nines are 81, and 81 into 4 is going to be a 4 with the unit digit. So 1764 is my answer. I will still try and solve it as much as possible. 9 fours are 36, and 36 multiplied by 50 minus 36 is going to be my answer. I have very smartly played that 49 has been split into 50 minus 1. Okay, so this is 1800, and if I do a minus 36 over here, I get the answer as 1764. Okay, I get the value as 176 and 4. Now, uh, as I promised, I would be coming to this question, and this question is nothing but a little long question. It's asking me how many perfect cubes are there between 1 and 1 lakh, 1 and 1 lakh, which are divisible by 7, which are divisible by 7. If I'm not talking about cubes, if I am not talking about, if I'm not talking about cubes, what am I looking for? Let's say that I'm talking about till, let's say 100, or let's say till 50. Okay, till 50. If I ask about all the numbers between 1 and 50 which are divisible by 7, what do I actually do about them? What do I do about them? I quietly play the table of 14, or the table of 7 in my head. 7 ones are 7, 7 twos are 14, 7 threes are 21, 7 fours are 28, 7 fives are 35, 7 six are 42, and 7 sevens are 49. Okay, 7 sevens are 49. So I can easily say that there are 1, 2, 3, 4, 5, 6, and 7. I have 7 multiples of 7 available between 1 to 50. But now I am talking only and only about perfect cubes. Okay, I'm only and only talking about perfect cubes. Just try and see what I'm talking about. Any number, any number which is a cube will have three will have three same looking numbers getting multiplied, or three same numbers getting multiplied. If A is a cube, then A is multiplied by itself 3 times. If B is a cube, B is multiplied by itself 3 times. Okay, so I've made this thing clear what a cube actually is. Let's say when I'm talking about 9, so 9 nine's cube is, I know the value is 729. But how do I know this is a cube? Because I know that 9 is multiplied by itself 3 times. So if in any number, if in any number which has to be divisible by 7, and it also has to be a cube, it has to be divisible by 7 cube as well. It has to be divisible by 7 cube as well. Then you'll tell me, that there is only one number, there is only one such number. Okay, you'll tell me that there is only one such number which, when multiplied by itself thrice, is lying between 1 and 1 lakh. But the story is not like this. But the story is not like this. What if I talk about 14 multiplied by 14 multiplied by 14? This would also be a number which would be divisible by 7. This would also be a number which would be divisible by 7. So, this means I'm wrong, and it's definitely well under 1 lakh. It is definitely well under 1 lakh. So I need to find out if 7 cube, 14 cube, 21 cube, then um, 28 cube, 35 cube, and 42 cube, and I think then 49 cube. Okay, so I have 7 of these numbers. I will not go beyond this. The reason why I won't go beyond this is because when 50 is multiplied by 50 is multiplied by 50, I reach a number which is nothing but 1,25,000. Okay, 1,25,000. And also, if I do a 49 cube, it is definitely going to be very close to, 1,25,000. So this 49 cube is also not going to be helpful to me. So if I wish to apply guesswork, then I can easily say that I have 1, 2, 3, 4, 5, and 6. I have 6 multiples available with me. I have 6 multiples available with me, which are less than 1 lakh and which are divisible by 7, and they are also cubes. I'll quickly do I'll quickly do a 49 cube. Okay, I'll quickly do a 49 cube. I have 49 cube with me. I have 49 cube with me, and the value of 49 cube, which is 1,17,649. Okay, 1,17,649. So this is also way above 1 lakh. What if I do a 42 multiplied by 42 multiplied by 42? So the value of 42 cube is nothing but 74,088. Okay, so this means I'm going to limit myself till 42, and I have 6 multiples of 7 which are cubes in nature, and they are also less than 42 cube, and which are also less than 1 lakh. So this was more of a conceptual question. So I hope you were able to understand why I said that this question is going to be pretty long, and I'll only solve it after solving this LCM question first. Okay, so I hope you've understood it. If you have any other doubt, please write it in the comments. Okay, now um now I'll be talking about AP and GP. There are very simple formulas which you need to memorize. Very simple formulas. I'll first talk about the formulas, and then I'll talk about the concept. The formula, the first one being the nth term, formula, which is the first formula that you're supposed to see. And the second formula which you're supposed to learn is that of sum. Okay. For the nth term, the formula is an is equal to a plus n minus 1 multiplied by d. The d stands for the common difference, n stands for the nth term, and h stands for the first term. What about the sum? For sum, Sn, it stands for n by 2 in the bracket 2a plus n minus 1 multiplied by d. 2a plus n minus 1 into d. For GP, the value of an is equal to a multiplied by r raised to the power n minus 1. R is nothing but the common ratio. The common ratio. What about Sn? The sum is a being the first term multiplied by 1 minus r raised to the power n whole upon 1 minus r. Okay. Also, if the number of terms are infinity, at that time Sn stands for a whole upon 1 minus r when the number of terms are infinity. Okay, or if it is an infinite GP. Now I'll tell you, as I've already like poured out all the AP and GP formulas which I had in mind. Now, if you find that there are numbers n and there is a summation of it, there is a summation of it. There is a summation of it. So we have sometimes we have terms with us, a few terms with us, okay, and most of them form a kind of series. Whenever we have a simple term which says 1, 2, 3, 4, and let's say it goes on till 10. At that time, you will not add each and every element together. What you will do is you will employ this formula. What does the formula say? The formula says n multiplied by n plus 1 whole upon 2. N multiplied by n plus 1 whole upon 2. Whenever you get this formula right, is that when you get the answer of this. Okay, let me quickly apply it for 10 terms. N is going to be the number of terms. So it's going to be 10 multiplied by 11 whole upon 2. This would give me the value or the final answer as 55. Okay. Similarly, there would be situations when you would get terms like 1 square, 2 square, 3 square, and so on till 10 square. So in such a situation, you need not add up the squares of each and every individual term. What you can actually do is you can use the formula of summation of n squares, where the formula says n into n plus 1 into 2n plus 1 whole by 6. Okay, n into n plus 1 into 2n plus 1 whole by 6, right? So let me apply the same formula for 10. So this would become 10 multiplied by 11 multiplied by 21 whole by 6. Okay, so there's 3 sevens are 21 and 2 fives are 10. 7 fives are 35, then 35 into 11, that is nothing but 385. My answer would be 385 for this. Okay, so I made myself pretty clear for n and for n square as well. But there might be a situation when you'll have to use 1 cube, 2 cube, 2 cube, 3 cube, 4 cube, and so on and so forth. In such a situation, what happens is you're going to employ a formula again. Okay, let's assume that it is going till 10 cube. What does the formula for cubes look like? The formula for cubes looks like this, that the summation of n cubes is equal to n into n plus 1 in bracket whole upon 2 and a whole square to this formula. Let me do that here as well. n multiplied by 11 whole upon 2 and then a square to this. This means 55, and 55 square is 25 over here, and then 5 6 are 30. 3025. Okay, we have 3025. So I hope I was able and I was successful in explaining you how summation of such terms goes along. Okay, I'll take a little more space and explain the basic concepts of AP. The basic concepts of AP. So what does AP mean over here? What does AP mean? AP means that I'm following an arithmetic progression. I'm following an arithmetic progression. Arithmetic progression. In an arithmetic progression, the kind of operations we do are going to be 2 plus or minus. Okay, there would not be any operation which involves multiplication, and certainly there won't be any operation which involves any exponents. So in arithmetic progression, you will have a series of terms. You will have a series of terms. In that series of terms, the term will start with a. The next term would be a plus d, and the next term after that would be a plus 2d, and so on and so on. It will go till a plus n minus 1 multiplied by d. You could have asked me, why does the last term not look like a plus n d? The answer to that is that the first term doesn't have any the first term doesn't have any source of difference. That means there is no term d involved in the first term. That is why in the last term, the involvement of d would be 1 less. Okay, so in the last term, the involvement of d would be 1 less. So this was just for conceptual understanding. This is not something which you must remember. Okay, so as I've already said, I'll quickly give you a small example. Let's say I have these numbers with me. I have 1, I have 4, then I have 7, I have 10, I have 13, I have 17, I have 20, and so on. So in such a situation, In such a situation, you would see that there is a progression of plus 3. There's a progression of plus 3 in every alternate term. In every alternate term, not in every alternate term, or the way every next term, there is a progression of 3 that is going on. So here, I would say that the first term, the first term is equal to 1, right? The first term is equal to 1. It's basically called A, or the starting term. It's basically called A, or the starting term. Okay, that is the first term. What about D over here? D is the difference between two consecutive terms. Let's call it A2 minus A1. This A, which from where it is starting, I can also call it A1, and I can call this term A2. So the difference between A2 minus A1, it is also going to be equal to the difference between A3 minus A2, which in this particular question stands for 3. Okay, it stands for 3. So I have the first term, I have this, and what does N stand for? N stands for the number of terms. N stands for the number of terms. Yep. So N stands for the number of terms. I hope we are good. Okay. So the formulas, you've already gotten to understand the formulas over here. If you need to find out the nth term, a plus n minus 1d. If you need to find out the sum of the terms, n by 2 in the bracket 2a plus n minus 1d. Similarly for GP, if you need to find the nth term or any term in this or any term in the equation, you get a multiplied by r raised to the power n minus 1, and sum of the terms is going to be a multiplied by 1 minus r raised to the power n whole upon 1 minus r raised to the power n. Okay, okay, I think we are good. Moving on, quickly solving this question for you. Find the nth term of the AP if the total number of terms are 15. I can clearly see that the first term over here starts from 1. The common difference is 4 minus 1 or 7 minus 4 or 10 minus 7. The common distance difference comes out to be 3. The last term of the sequence n is 15. I need to find out the last term. Okay. So the nth term is nothing but a15 is equal to a plus n minus 1 into t. The value of a over here is 1. The value of n is 15. 15 minus 1, and the value of d is 3. So I'll get my answer as 1 plus 15 minus 1 is 14. 14 multiplied by 3. 14 3s are 42, and 43 is my answer. Okay, 43 is my answer. All right, so I'll move on. Yep. Now it is asking me to find out the sum of the AP. As I've already said, whenever you find a number in this particular series where the difference is equal to 1, you can simply apply the formula of n into n minus n plus 1, n into n plus 1 whole upon 2. This would give you the sum of n terms in a series. So I'll apply that. N is the 15th term. So 15 multiplied by 16 whole upon 2. This would give you 120. And this 120 is the sum. Okay, this 120 is the sum of the AP. But just because I knew this formula doesn't mean that I'll apply it all the time. I will apply the second kind of a formula. Okay, I'll apply the second kind of formula, the long formula. I'll use the value of Sn. The value of Sn is equal to Sn is equal to n by 2 in the bracket 2 times of A plus n minus 1 multiplied by D. Okay, 2A plus n minus 1 multiplied by D. What does n by 2 stand for? What does n by 2 stand for? N stands for 15 and by 2 is going to be here. What does 2a stand for? 2a stands for 2 multiplied by 1, which is equal to 2. What does n is 15 over here? So 15 comes as 14, and 14 would be multiplied by the common difference, which is nothing but equal to 1. Okay, so this is 14 plus 2, this is 16. So this comes back to the same point where we all started. 15 into 16 whole upon 2. 15 into 16 whole upon 2. So I have 2 ones are 2. I have 2 eights are 16 and 15 eights are 120. Okay. So both the results are same. You can either go from this way or you can go with this method. Just because we are trying to understand the concept of AP, that is why I went with the longer method. But this shortcut, this short trick is available to me. Moving on. What is the first, if the first term is 10 and the common ratio is 3, then write the first 5 terms of the GP. Okay, this is a simpler question that I'm going to tackle, but I'll first try to explain to you what GP actually stands for. GP stands for geometric progression. GP stands for geometric progression. What happens in a geometric progression? In a geometric progression, let's say I have a number 1 over here, then I have a number 3 over here, then I have 9, then I have 27, then I have 81, then I have 243. So the difference between two terms, or the additive difference. What does the additive difference mean? That what is the difference between 3 minus 1? It is 2. What is 9 and 3? This is 6. What is 27 and 9? This is 18. What is 81 minus 27? I think that is 4. 54, yeah, that's 54. So that's 54. So the additive difference which I can see, or what is being added to each and every term, is not uniform. So these kind of series do not call themselves or do not qualify to become GPs. Okay, they do not qualify to become GPs. So what is the kind of a series which qualify itself to become a geometric progression? In geometric progressions, there are multiplications that occur. Okay, there are multiplications or divisions that occur. And how do we actually find them out? I'll first tell you what these terms are called: a2, a3, a4, a5 and a6. See, if this term is a GP, then the common difference or the common ratio would not be represented by a2 minus a1. It would rather be represented by a2 upon a1. Similarly, a3 upon a2, and similarly a4 upon a5. No, this is a4 upon a3. a4 upon a3, and similarly a5 upon a4. Okay, a5 upon a4, a5 upon a4. Now let me quickly check that out for you. 3 upon 1 is equal to 3. 9 upon 3, when I cancel it out, 3 ones are 3, 3 threes are 9. Similarly, 27 upon 9, 9 ones are 9 threes are. Similarly, 81 upon 27, this is 27, 27 ones are 27 threes are. Similarly, 243 upon 81, 81 ones are 81 threes are. So I can find out that the ratio is common in nature. The ratio is common in nature, which is nothing but equal to 3. Nothing but equal to 3. Right? Am I right? I think I'm completely right. Okay, let me move on and let me take you to the question again. If the first term is 10 and the common ratio is 3, then write the first 5 terms of the GP. This means that the first term was 10, the common ratio means 3, and the common ratio is usually multiplied. The common ratio is usually multiplied. This means 10 would be multiplied by 3. This would give me a 30. And then I need to write the first 5 terms. This is the first one, second one, third, fourth, and fifth. Okay, so 3 would be multiplied in each consecutive term. This is going to be 90, this is going to be 270, and this is going to be what? 810. So I've written down the first 5 terms of the GP as was asked in the question. Okay, okay, I hope we're good. Let's move forward. Let's take things forward. Yep. find the sum of the GP. This is the same GP out of which the first five terms which we calculated. Okay. So this is basically asking us to find out Sn. Where will I see the formula for Sn? I will see the formula of Sn here. Here. Where did I write it? Yep, here. Sn is A multiplied by A multiplied by 1 minus R raised to the power n whole upon 1 minus R. Okay. I'll quickly write it down. This is A multiplied by 1 minus R raised to the power n whole upon 1 minus R. See, the value of R which we have here, the value of R that we have here, it is 30 upon 10. I can simply call the value of R as 3. The value of A which we have is equal to 10. So 10 would be multiplied by, and the number of terms I left it behind. The number of terms is equal to 5. So 10 multiplied by 1 minus R, the value of R is 3, and it has to be raised to the power n, which is 5 whole upon 1 minus 3. So 1 minus R raised to the power n, this is a faulty equation. Why is it a faulty equation? Because we would get negative outputs out of it. So R raised to the power n minus 1 is also useful, whole upon R minus 1 is also going to be useful. These can be interchanged because we have a minus sign over here, and the minus sign would ultimately get cut off. But just to help people not getting scared about whatever is going on, I will put it this way. Okay, so 10 multiplied by 3 raised to the power 5. What does 3 raised to the power 5 stand for? 3 3s are 9, 3 9s are 27, and 27, this is 81, this is square, this is cube, this is 4, and 5 is 243. Okay, so 243, I have 243 minus 1 whole upon 3 minus 1. Okay, so this would give me 242 multiplied by 5. So I'll quickly do it. 242 multiplied by 5, this would give me 1210 as my answer. Okay, this would give me 1210 as my answer. Yep, I think we are good to go. Moving to the next question, and this is also the second last question of the equation. What is the sum of all natural numbers between 100 and 400 which are divisible by 13? Whenever you get such a question, you need to find out the closest number above 100 and the closest number below 400. Okay, and both of them should have a common property. They should be divisible by 13. Okay, I'll quickly run through the table of 13. 13 sevens are 91, 13 eights are 104. Okay, so 13 eights are 104. So 104 is my first term, which is A. Okay, now I'll reach the last term or the nth term, which would be the nth term. So I'll quickly try to divide it. 13 3s are 39, then I have a 10, and I have a 10. That 10 could have been 0, so I could call it 390. I'll reduce the 10 out of 400 to make it divisible by 13. So 390 is divisible, and this is my nth term or last term. There is a small formula which I would now like to introduce because we are at a juncture where I believe it can be introduced. Sn is equal to n by 2 in the bracket a plus l. A plus l. If I need to find out the value of 390 or which term 390 is, so I could have easily written that the value of 390 is a plus n minus 1 into d. In my bigger formula, Sn stands for n by 2 in the bracket a plus n minus 1 into d. A plus a into n minus 1 into d. So I'm doing nothing. I'm just replacing this part of the equation. I'm just replacing this part of the equation with the formula of an, or this an can also stand for the last term. Okay, so I'll use a much shorter formula as I was expecting. I also need to find out the number of terms that are going to be between 104 and 390. 13 8s are 104 and 13 30s are 390. So between 390 and 8, there are 23 terms. There are 23 terms. I won't call them 22 terms because I have to count. I have to add one more to them. Okay. So the number of terms which I have are 23 whole divided by 2 and a plus l. What does a stand for? 104. What does the last term stand for? 390. Okay. So it will come down to 494 into 23 whole upon 2. 2 ones are 2, 2 twos are 4, 2 fours are 8, and 2 sevens are 14. So 247 into 231 would be my answer, would be the answer that I'm looking for. Okay, so I hope you've understood the concept, and the concept is the main thing. In the exam, you will get 4 options. Out of the 4 options, multiply 3 and 7. 7 3s are 21. The unit digit is 1. Okay, the region is, sorry, the unit digit is going to be 1. Got it? I think we are good. Now, this brings us to the second last question of our entire course on number systems. The first one being, these terms are getting added up till it becomes this point. Till it becomes this point. Yeah. In this question, you would see that there is a very peculiar pattern that you would notice. And that pattern is that this might seem to be a difficult question at first, but in reality it is much easier. You just try to solve the first term. The first term says 100 square minus 99 square. So the formula that will be applied over here is a square minus b square. The value of a square minus b square is a plus b, and then which would be multiplied by a minus b. A plus b is 100 plus 99, and a minus b is 100 minus 99, which is equal to 1. So the term that I get out of it is 199. Similarly, if I do it for 98 square minus 97 square, I would come down to 98 plus 97, 98 plus 97, which is 5, and this is 195, and it would be multiplied by 1. So my answer would come out to be 195. Okay, the answer would come out to be 195. Similarly, I'll just do it for the last time one more time. 97 square minus 96 square. No, it's not 97 minus 96. It is actually 96 minus 95. 96 square minus 95 square. So 96 plus 95 would come out to be 191 multiplied by 1. And this term would be 191. Okay, this term would be 190. Yep. Okay. Yep. So I can easily see that the pattern that is being formed over here is that of 199, 195, 191, and so on. What is the last term in this equation? What is the last term in this equation? The last term in this equation is 2 square minus 1 square. 2 square minus 1 square is 2 plus 1, which is equal to 3, and 2 minus 1, which is equal to 1. So the last term in this equation is I need to find out the sum. Okay, I need to find out the sum. Every consecutive term has a difference of 4. Has a difference of 4. Okay, so what you can do is you can either take it in the unconventional direction, because the differences is going to be -4 from this side, but if we calculate things from the right hand side, the difference are going to be +4. So I can consider my first term to be 3, or I can consider my first term to be 199. Okay, so let me quickly do what can be done about this. So the sum of n terms is equal to a plus l multiplied by n by 2. I've already helped you with this. So a means 3, l means 199, and n by 2. So I'll have to know what is actually the nth term. The nth term is 199, and for 199 I need to check if a is 3 plus n minus 1. I need to find out what that is, and d is 4. Okay, d is not 4, d is actually, yeah, d is 4 here. So I'll subtract this from here. 196 upon 4. 4 4s is 16, and 4 9s are 36. 4 4s are 16, and 4 9s are 36, is equal to n minus 1. So the value of n comes out to be 50. I'll quickly put this value 50 over here and multiply it by 50 by 2. Okay, so 199 plus 3 turns out to be 202 upon 2 into 50. 202 upon 2 into 50. This becomes 101. 101 means 5050 is my answer to this question. 5050 is the answer to the question. Okay, I hope I have told you the formulas multiple times. Okay, just follow the formula, and this calculation part is something which I expect you to do on your own. Okay, the formula part is clear, and this calculation portion is something which I expect you to do on your own. All right, coming to the last question. How many terms of the series must be taken so that the sum of all the terms is equal to 45? The sum of all the terms is equal to 45. The first term being -9, the second one being -6, the third one being -3, and so on. I need to find what is the nth term if the sum of all the terms is equal to 45. Let me quickly find out the common difference. The common difference seems to be +3. Yep, that is +3. So I have the d as +3. I have the n. Which I need to find out. I have the a, which is equal to -9, and I have the sum with me. Sum is equal to 45. I'll quickly put them into play. Sn is equal to 45 is equal to n by 2. That needs to be found out. In the bracket, 2a is -18 plus n minus 1 multiplied by 3 plus n minus 1 multiplied by 3. So I'll put it up as 90. 90 is equal to n multiplied by 3n minus 3 minus 18. Okay, so this would become 3n minus 21, and there would be an n over here, and this would be 90. I have four options with me. Okay, these four options need to be culminated. How do I choose out of these four options? I'll quickly try to put them in place. I already have an n over here. And there is a 0 as well. So this means either this or this should be equal to 10. So I'll choose the first option first. I'll put 10 over here. Then I'll apply 10 here. 3 tens are 30. 30 minus 21. And voila. 10 multiplied by 9 is 90. And by using hit and try, I got the answer. But if I still want to go the longer route and I wish to be a little more laborious, what I would do is I would create a quadratic equation out of it. 21n is equal to, yep, minus 90 is equal to 0. I'll have to split up the middle term. I have 270. I have 270, and the difference between the two numbers which make up 270 has to be 21. So I have 3 and 9. Yep. So what I can do is I can split them up in 30 and 9. I can split them up in 30 and 9. Okay, 30 and 9. That will help me out. 3n square minus 30n plus 9 minus 90 is equal to 0. From this, you would get the value of n is equal to 10. I'll still solve it a little more. I'll say 3n. I will have n minus 10 plus, this is n over here, plus 9, and this is n minus 10. I can clearly see that n minus 10 is equal to 0. So the value of n is going to be 10. Okay. So I hope the entire chapter was very, very interesting. It took us a very long time because we don't teach in a manner which leaves behind people, or it is only for the well versed people. It's for both the people, both the kind of peoples, the ones who don't know much and the ones who know a lot. Okay, both of them would be benefited equally. So thank you so much.